Yesterday was a great day for Latvia as Latvian Parliament adopted the CO2 storage breakthrough, namely allowing CO2 storage in Latvian soil. And today, first speaker will be also from Latvia. And maybe that is the way how we can try to connect dots for one, let's say, pilot territory. And keynote speak will be given by Krists Martens, who is one of the key people in Brocēni cement plant. Švenk Latvia will share us their very consistent and already long-lasting CCS project deployment status and how it goes.
Right. Thank you, Jans. Good morning. Good morning to all of you here and also those who have joined us online. In next 15 minutes, I will talk more about recent developments, mostly. Or project recent developments, but some background. Schwenk Group is German-owned family company, owns several cement plants, and most of them are located in the EU, but then there are also some more exotic locations like in Southern Africa. Cement production is very CO2 intensive. We emit roughly 850,000 tons of CO2 per annum. 1/3 of these emissions come from fuel combustion. 2/3 of these emissions come from the processes for cement production, namely limestone burning. So speaking about the CO2 reduction, Schwenk has its decarbonization strategy, 3 main goals. First goal is to reduce the average emission factor in the clinker production. Second goal is to reduce the average clinker factor in cement itself. But with that, it's not enough. We still have lots of CO2 then remaining, and for that, for the hard to abate industries, there are not really much alternatives as to carbon capture, because we cannot electrify our processes, and the CO2 is our byproduct. So speaking about the project development, so in order to succeed in our efforts to decarbonize cement production, first thing what we did and what was very important is that we established a consortium that is focusing on the value chain development together with our sister company Akmenės Cementas and Lithuanian KN Energies, as well as 2 Japanese shipping companies. And then at the end of, or rather beginning of 2024, we got the PCA status, so project of common interest, in order to apply also for some EU funding for the project. So the idea is that we transport CO2 from 2 emission points, so Švenk Latvia cement plant and then also Akmenės Cementas cement production plant, transport the CO2 to Klaipėdas port and then offshore. What else has happened then? Since then, we began the second half of last year, we began our pre-feed studies for the carbon capture plant, and also began the work on the Innovation Fund application preparation. We submitted the application this spring in April. Now we are waiting for the results. Hopefully we will get to know what is the outcome of that soon. And yeah, we finished the pre-feed studies for the plant. In fact, we did two studies instead of one for the de-risking purposes, given that the overall project cost varies between 500 to 800 million euros. We have to make sure that we have done everything as we should, as we must, to make sure that we do not have any regrets later on. And yeah, we also finished the pre-feeds for the transport towards Klaipėda port. And one other significant development this year that is still continuing is that there was a decision made by the Schwenk Group to choose Latvia Brocēni as the different CO2 capture technology test platform. So instead of just testing the technology that we are focusing on, we are actually now doing tests of different technologies. Currently it's two, so Norwegian Capsol Go, which is HPC-based technology, chemical process, and then there is also Svante, which is Canadian, which is building their technology on this so-called MOF, or Metal Organic Framework. Here's also some pictures of the inauguration just a month ago. In the middle here, we also have a Prime Minister of Latvia, along with some other high-level state officials. That also indicates interest from the government side to support with the project development. And as Jānis also mentioned into the introductory part, then yeah, we also see some real actions in that regard as well. So besides that, one other big development that was announced just a couple of weeks ago, Schwenk, through its affiliate Carbon Vault in Denmark, entered into the partnership with Total Energies for Bifrost CCS project. A bit more about that. So the location of the offshore plant is in Danish North Sea, roughly 200 kilometers west from Denmark's coast. Storage capacity is estimated to be up to 335 million metric tons over 35 years of its operation. And injection capacity is expected to reach up to 5 million tons per annum when at full capacity. So yeah, key partners, Total Energy as an operator, 45%, Schwenk Group through its affiliate as a partner, 35%, and then the Danish state-owned entity, Nord Sofonden, 20%. What's been done so far with the project is that, I hope you all can see it, so the initial studies have been done, seismic has been done, and reservoir suitability has been confirmed for at least the depleted gas field that is part of the Bifrost project. And when it comes to the operations, then the target is for the storage to start its operations from 2030, which well matches also with the Schwenk Latvia plan to deploy the CCS CC unit. So looking then in future, the next step would be to initiate now the feed studies for Brocēni CC and also for the value chains further development. We have not yet begun this feed study for the carbon capture part simply because we are waiting really on the innovation fund. We have applied for 150 million euros which is not a small amount of money, and we really need to see first whether we get any grant or not before making any further actions. Yet, as a side note, that does not mean that it might be a showstopper if the decision is negative. And then, yes, in the second half of 2026, we should complete the feeds. And also by that time, we should also have the EPC contractor selected. So. Right. So after that, in 2027, or as soon as possible, we make a FID, and afterwards, the construction work can begin. After which, then the testing and start of the plant itself. And as the last slide, you can see here how the visual the plant look like. So this is HPC based plant visualization. So starting from the flue gas pre-treatment, ending with the liquefaction, and then preparation for further transport of CO2. So yeah, that's from my side this morning. Thank you.
Questions? Here we go.
Thank you very much. It was very interesting. Perhaps a very stupid question for this morning to start the discussion. You mentioned Klaipėda, right? If I'm not mistaken. And why wouldn't that be easier to transport it to the Latvian port? Because Klaipėda is in Lithuania, and then you have to. Maybe I missed something, but if you could explain it, why is it Lithuanian port and not a Latvian one? Like, I don't know, Ventspils or Liepaja or something like that.
Yeah, thank you for the question. The very short answer is Lithuanians were more proactive at the time when we started the discussions about the value chain development. But yeah, we see also that some other developers are now catching up. For instance, Liepaja, there is a developer who is interested in synthetic aviation fuel production. They are also interested in transport of CO2 offshore. So we remain open to all possible options. For us, it's about a matter of time and cost.
Thank you, Chris. I have two questions. One is regarding, so we heard that yesterday there was good news in terms of changing laws in Latvia. So does that, in terms of storage, changes any perspective, especially the carbon capture storage part? Because Latvia has potential for storage as well.
Yeah. It's too early to comment anything on the onshore, but what we see is that there is really attention from the policymaker perspective, and we've been also promised that there soon should be an informative report submitted to the Cabinet of Ministers that would basically describe then the CCS value chains development in Latvia, and basically should serve then as a basis for further subsequent actions that must be taken in order to even end up with onshore in Latvia. But yeah, too early to comment on that.
Okay, and my second question is regarding the project you spoke about with Total Energies. It's like right now just in study phases, or is it like already have commitment from both all the three parties which are there? You did mention like 45% Total Energy. So is it possible to explain what's the status right now? Is it
so? Schwenk Group, through its affiliate Carbon Vault in Belgium, in Denmark, has expressed its willingness to acquire 35% in the project. So they have an agreement in place, but now they are waiting on the authorities to get a green light, basically.
More questions? Not this morning. All right.
Thank you.
Thank you, Chris. All right. Then we have time for first session today that will dive into new technologies and recent advancements in CCS. And first first presentation will be given by Hanna Menke. The name of the talk is Artificial Intelligence and Digital Twins and CO2 Storage. Hey, floor is yours.
All right. So thank you very much for inviting me to speak today. So my name is Hanna Menke. I'm an associate professor at Heriot-Watt University, and I work with quite a large group of talented people. So this is not all my work. But today I'm just going to give you a flavor of some of the ways we're trying to apply AI and machine learning for CO2 storage. So when we look at this very classical diagram of CO2 storage, right, we have several different types of issues and things we need to understand better in order to predict it more efficiently, right? So we have these residual trapping, this multi-phase flow going on, and we also have dissolved CO2. And if your reservoir is made of a carbonate, for instance, that dissolved CO2 can then dissolve the reservoir itself. So you need to understand how these processes are interacting, and in order to do that, you can see you're zooming in here. All of these processes are actually happening at the scale of grains and pores. And so that's what most of my research looks at, is how we can better predict these processes at the pore scale, and then how we can upscale them. And so today I'm just going to give you 4 quick and not particularly detailed examples of how we are looking at these pore scale characterizations of these different processes and how we're trying to upscale them. So first, we have reactive transport solvers. This is reactive dissolution. So you have CO2 saturated brine going through your pore space. The pore boundaries are delineated by lines, but these are actually not blocking the flow. They're just an overlay. And the high flow rate fluid channels, the sides of the channels are reacted and dissolved. These grains are dissolved. And this changes the porosity permeability relationship of the reservoir. It can be structurally damaging if you dissolve too much. So we really want to understand this better. And with our pore scale models, it's very easy in pore scale modeling to predict the concentration field, predict the flow rate. But actually changing the boundaries, actually dissolving the grains, this is really, really computationally expensive. So we wanted to look at if with machine learning, we could make this faster. And so we have these machine learning models. They're called convolutional neural networks. It would be let's say, when in ChatGPT you ask it to create an image for you, that's what it's doing. It's using a convolutional neural network to output the image that you asked for. So for us, we ran a few of our very computationally expensive simulations, and we wanted to know, can we use these convolutional neural networks to predict, just from a porosity field, predict everything that a model would give us through time. So we took a first crack at it, and what we found was that actually, just out of the box, these models really struggle. Even for our most advanced convolutional networks, the results are not very good, right? So this is the ground truth. This is what the concentration field should look like, and then this is what it looks like coming out of the convolutional neural network, even with full training. And then on the right, that's the error. So you can see there's quite a lot of it. So what we did was we designed another convolutional network to predict the error and its correction. And so we found that by stacking the first network and then corrective networks on top of that, we eventually would asymptotically approach the correct answer. So and so with this model stacking and this corrective process, we were able to get 100 time steps in the future. So this is not 100 numerical time steps, this is 100 output time steps. So really far into this dissolution process at an accuracy of about 94%, while going 2 to 3 orders of magnitude faster than our usual numerical models. But this is dissolution on the pore scale. And in order to really be able to use it at the reservoir scale, we need to find some way of extracting these properties that can inform our larger scale models, right? And depending on the reaction rate, so that's how much CO2 is dissolved in the brine, and the flow rate, how fast it's moving, this really changes the type of dissolution and how the porosity permeability changes. So for here, it's kind of eating away at the face. Over here, it's dissolving everywhere at once. And then in the middle, you actually get what's called wormholes. So they eat their way through the rock. And like near the wellbore, this could be particularly dangerous because you could just basically eat the entire area around the wellbore and cause serious formation damage. So it's really important to be able to predict these at the reservoir scale. And so we had a master student who looked into this for us. And he typically in reservoir models, you just use one porosity permeability relationship. You pick one, you use typically something like Kozeny-Kármán, a power law relationship. This is how it's going to dissolve everywhere. And if you have one type of relationship, you get a model that predicts this type, maybe these little small wormholes. Or if you use another relationship, you get a slightly different one. And these are vastly different predictions, but are they accurate? And our argument is, well, actually, using one is not good enough, right? Whether you're at the tip of the wormhole, in the middle of the wormhole, or out where there is no wormhole, actually, the porosity permeability relationship that's evolving is evolving differently. So we thought we could use AI, train a model to predict based on the local porosity, permeability, reaction rate, and velocity to predict exactly how that particular part of the model is evolving at the Darcy scale to improve our predictions. And so that's exactly what we did. So you can't take an image at the pore scale and feed it into a reservoir model. It doesn't understand those properties, right? These reservoir models are built on the Darcy scale. So all you can take is like a single point from this image, right? So you can calculate its porosity, you can calculate its permeability, you know its average velocity, average reaction rate. You can use that to feed into, in this case it's a decision tree, to output what the next permeability would be. So we trained a model to do this. And we compared it to, so this is a huge pore scale simulation. This is like, something like 10,000 by 10,000 grid blocks, so really, really big. This was done on a supercomputer. So this is our ground truth. We compare it to what you would usually do, just take one relationship and apply it everywhere, versus a machine learning model that's trained based on the local properties in the model to predict the evolution of permeability. And what we found was that when we're solidly in a regime, like compact dissolution, phase dissolution, the machine learning model doesn't actually provide all that much value, right? Which makes sense because that is when you're solidly in a regime, that is exactly one relationship. But when you're on the edges, when you're doing something, when you're in like in a conical wormhole, or when you're channeling but you're not quite uniform, actually the machine learning model does a lot better at predicting what the Darcy scale properties would be in the reservoir. So now I'm gonna switch gears a little bit and talk about multi-phase flow. And so this is a data set out of Stanford. They ran a whole bunch of reservoir scale simulations looking at the saturation and the plume migration in a CO2 reservoir, and then they tried to predict it with machine learning. And their method was a UFNO, which is U-shaped Fourier neural operators. It's a type of convolutional neural network that works in Fourier space. That's not important, but the results were okay. They're by no means bad, but we thought to ourselves, I bet we could improve them. So maybe this was hubris, but we we gave it a go. And so what we found is that the way they trained it was a bit confusing to the model, and it was leading to results that weren't as good as they could be. And so what they had done is they took a whole bunch of input fields, so the porosity, the permeability, saturation, but they also added fields like time and like flow rate as an image. And this is very confusing to a model because you have a parameter that varies in space and then a parameter that doesn't. So we managed to disentangle these. So we have the spatial features as one input and the scalar variables as another input in what's called a film layer injected into the model. And by disentangling these, the model is able to focus on learning the features that actually do change spatially. And with this, we're able to increase the accuracy of our prediction to 97% and decrease the model error significantly. And what's great about these trained networks is that they're 100 times faster than Eclipse simulations, which means that you can make a whole bunch of predictions, and it really allows you to do uncertainty quantification in a very efficient way. And so the last example I'm going to give is relevant to special core analysis. So I work in the field of pore scale imaging, and traditionally in the oil and gas industry, in carbon storage, we do, in order to get a relative permeability for a field, we would do special core analysis. And this is very, very expensive, takes a lot of technical expertise. A lot of things can go wrong, especially in CCS, where you can have reactions that you weren't necessarily expecting. So you want to minimize the amount of time you spend doing this. And recently, there has been a lot of advancements in imaging techniques. So you can actually take an image of a core, and you'd be able to see its grains. So the question is, can you then simulate on that in a way that would be representative of what would happen during special core analysis and be able to upscale that into something that's reasonable for putting relative permeability parameters into your model accurately. And so towards that end, we wanted to be able to take these images and then simulate on them. And so we built a multi-scale pore network model that essentially is able to take something like a multi-scale carbonate, the pores you can see, these are the nodes, and the microporosity, the sub-resolution porosity, is a Darcy phase. And so this is it's not a new type of pore network model, but we didn't have an open source version, so we made one. But there's a question here. If you have these sub-resolution phases that you're assigning Darcy properties to, how do you know what to assign them? And if you have a result from a special core analysis, if you have a rel perm, it's reasonably easy to essentially history match this. Pick the right value for that phase, and you'll be able to run the simulation, compare it with the result and the experimental result, and then sort of iterate towards that. But carbonate rocks aren't that simple. There's not just one phase of microporosity. There are many. And so we wanted to find a way to assign the relative permeability values of the different microporous phases in such a way that we could then history match a real core to a real experimental result. So with micro-CT imaging, you can take images, but there is a limitation in that you have a trade-off between the field of view and resolution. So you can't scan the whole sample at really, really high resolution. You'd have to cut it up into sections, you'd have to destroy it, it would take millions of dollars, millions of hours just for one single core. So what we did was we created a data set based on a single high resolution scan. We cut it up into subsections and used regular pore network modeling. So this is without any sub-resolution phases. You can see everything, and you can get a relative permeability for each subsection. And with that database, we are then able to combine it with a dense neural network and ESMDA, which stands for Ensemble Smoother with Multiple Data Assimilation. This is, I know it sounds very, very complicated, but actually this is something that's used and has been used in reservoir scale modeling for a while. We're just the first people to use it at the pore scale, to my knowledge. And what it is it's a Bayesian updating algorithm. So it combines what you think you know, a prior model, with what you measure, which is experimental data, right? To estimate the true properties of your system. So you start with guesses. That's the ensemble. You create a bunch of possible models. For example, in our example, different values of microporosity parameters like capillary entry pressure or relative permeability coefficients. And each model is one member of the ensemble. Then you run your forward model. So for each ensemble member, you simulate what would happen experimentally with this multi-scale pore network model. And then you compare it with the real data. And you look at the difference between each, and then you update the guesses, right? So you converge on the correct answer. And what the ESMDA does is it adjusts all the model parameters using those differences and nudges them towards the model that better reproduces the observed data. And you repeat this several times, slightly inflating the data so it doesn't overfit too quickly. And after several iterations, you can now get a probability distribution of parameters that fit the data. And this is very clever because it gives you both a best fit prediction, which is the mean, and also an uncertainty estimate. And so with this, we are able to reproduce our experimental results with high accuracy. And once you have that, you can then apply it to other rocks that you don't have an experimental result with, and thus save a lot of time and money. And so finally, to conclude, our next challenge that we're looking at is pore scale supercritical CO2 plume migration. So this is a simulation of injecting supercritical CO2 into a pore space. It's incredibly computationally expensive, and it's also very, very hard to predict, and we tried. And so we have 600 or so simulations of this. We clogged up our cluster for a couple of months, and what we've done is we've uploaded it as a benchmark data set for the community as a challenge to them. So I'm looking at you, Parsa. This is and so we've created, and we made it reasonably easy for people. We have introductory examples. It's all in Jupyter Notebook. You don't have to do any pre-processing. The training and inference steps are there. But our challenge to the community is, can you modify it to create a better result? And so this is up on Dryad, the data set of a whole bunch of different realizations of CO2 injection into different heterogeneities of rock. So I look forward to next year when somebody solves this problem for us. So thank you all for listening, and I'd be happy to answer any questions.
Questions to Hanna? Two usual suspects.
Thank you very much. That was really interesting. I'm completely outside of my sort of scope and area of expertise, but would something similar or something of similar complexity be applicable to the CO2 storage in depleted hydrocarbon fields, or those are just, too simple and you don't need any simulations, and just because this,
What do you, or like which part of it you can?
Let's say depleted gas fields, because you can also store CO2 there. If you don't have deep saline aquifers to store CO2, would something like that be also needed to,
It depends on what your. So I assume you're talking about the ESMDA. Yeah, or any of it.
For instance, I don't know. Again, not really something I'm dealing with, but
yeah, you have to have the data set, right? That's the thing with machine learning. You have to have a training data set, but. Depleted gas fields, it's not multi-phase, so it may be simpler. You might not need it. But as long as you have some sort of training data set, whether that's experimental or numerical, you can apply techniques like this to improve your results or to do your uncertainty quantification.
So would it be right to basically assume that sort of all the data processing for depleted hydrocarbon fields will be just like cheaper and not that complicated, because the formations, the geological formations, them as geological formations are just less complex? Or
I think this is going to be field dependent. I can't make a generalization about whether the complexity is going to be less, because all sorts of things could be happening, right?
Maybe I could add to this question. You're right, maybe, but you could probably have to spend less data of like depleted gas field or oil field for something like this. But at the same time, I think what Hanna was talking about, if I understood everything correctly, it's about CO2 injection, and that probably has not been seen in the reservoir before. So it might not behave in the same way as gas or hydrocarbons would have behaved. So if I understood, you talked about dissolution, so there could be some chemical effect of CO2 which
yeah,
could...
and it really depends on what the reservoir is made of. So if it's a carbonate, you're going to see dissolution. That's almost unavoidable.
Yeah, so data will be needed for that purposes. That's what I understood. But I think if I understood correctly, the talk was more about, okay, if you do this, you save time and money, right? That's the main impact.
That's the takeaway, yeah.
But at the same time, you did also mention that to do these computations are computationally very expensive. You have to use clusters. Does that cost offsets the cost of a conventional program to get data?
I would say for the pore scale simulations like that, that's more of a fundamental physics problem, right? So we're really trying to study the physics itself, right? So that computational cost is going to be far greater. But when you're talking about the upscaling and the reservoir scale models, I think, and also the SCAL, like replacing SCAL, I think that will be particularly valuable for saving money and time.
And are you aware? Does anybody has done this kind of comparison, like in terms of, let's say, doing a SCAL versus data collection using these kind of methods, machine learning?
No, I think this is the first that we know of. Yeah.
Thank you.
Very cool. We certainly hope to see you in some of the next Baltic Carbon forums to see advancements. Now, thank you, Hanna, for your presentation. And I will invite to the stage Shruti Malik. She's postdoctoral researcher at the Kaunas Technical University. And her title will be, for the presentation, Pore and Field Scale Computational Simulation of CO2 Subsurface Storage.
Hello, good morning everyone. My name is Shruti. So today I'm going to talk about the pore and field scale computational simulation. So this work is actually divided into two parts. One would be the experimental part and another would be the simulation part. So to begin with, we all know about the lithology or the geological structures of the Baltic region. We know that the Baltic basin extends from Estonia to Lithuania, and out of those three countries, the Baltic countries, Estonia does not have enough structures, and the structures are mainly present in Latvia and Lithuania, which are suitable for storing CO2. So they are deep enough to store CO2 in them. So with the research, what my research was, it starts from the field scale. First step was to understand the Lithuanian reservoirs and their storage capacity. Then we moved on to collecting some data to get into a deeper detail of those reservoirs, followed by some core scale experiments. Then we moved on to the pore scale to understand how it behaves at the pore level, and finally would move on to the pore scale simulation. So it starts from field scale to the pore scale. So for the field scale, the first step was to understand how feasible are the Lithuanian reservoirs for storing CO2 in them. There have been some work done where the researchers have tried to understand the storage capacity of these reservoirs, and they have presented a preliminary estimation of the storage capacity. So for our work, we took some Lithuanian reservoirs. There are two onshore reservoirs which are saline aquifers. They are Sidurai and Vaskai. And there is a depleted hydrocarbon zone in Lithuania, which is the Gargzadai zone. And it has around 8 depleted reservoirs in them, which could be utilized for storing CO2. So for our work, we considered the uncertainty principle, where we know that in the subsurface, we cannot take just one particular porosity value and we say that it is for the whole reservoir. There is uncertainty in the subsurface. So to take into account of that uncertainty, we took 3 cases: mid case, low case, and high case, where mid case was the one where we took the properties of the subsurface from the literature, what other researchers have utilized to determine the storage capacity, and we designed 2 cases. One is the low case, where we assumed that the properties are around 30% lower than the mid value, and another was the high case, where we assumed that the properties are at least 10% higher than the mid value, so that we could get a range of those properties and we could understand that what could be the minimum to the maximum storage capacity of these reservoirs. So we found that for the Sidurai saline aquifer, the storage capacity ranges from 54 million ton to 232. For Vaskai, it starts from 25 to 106, whereas for Gargzadai, it is from 64 to 267. So this was the first step where we understood that, okay, there are reservoirs which have the capacity to store CO2 in them. Now the next step was to collect the data from these reservoirs and get into a deeper detail. So for that, we went to the Geological Survey of Lithuania. We collected some core samples from Sidurai for the Vaskai aquifer, also from the depleted reservoirs of the Lithuania. One is the Pitušė, Vilkyčė. We did some XRD analysis of those those core samples to understand the mineralogy of them. Then we did another part was the collection of analogous samples. So we had reservoir samples and we had the analogous samples. And from those analogous samples, again, for the same thing we did, we took we did some measurements, we estimated their properties, we did the XRD analysis. So we had 2 sets of samples. One was from reservoir, another was from, the properties of these analogous samples is similar to the properties of the Lithuanian samples in terms of their porosity, permeability, their mineralogy. So another next step we did was the core flooding experiment. So for the core flooding experiment, we were trying to understand that if we inject CO2 through those core samples, how are they going to behave and how are they going to affect the properties of the sample. So for that, these experiments were conducted at Texas A&M University in Qatar. So for the core flooding experiment, we took the core sample, we saturated in a brine solution. The brine solution primarily was made of the salinity of Lithuanian reservoirs. So it was around 12% and around 18%. So these two were the salinities that we took for preparing the brine solution. So first, the sample was completely saturated in the brine under vacuum overnight. And then we moved this core sample into the core holder. And there was an accumulator. Accumulator is the one which holds the brine solution. So this first step was, after completely saturating the core sample, the first step was to inject again brine through the sample and determine the permeability of the rock sample. After injecting brine through the core sample, we immediately injected CO2 through it, and another next step was again after injecting CO2 we injected brine. So it was like a cyclic injection that we performed in order to understand how CO2 is affecting the core sample. So what we found was that CO2 is reducing the permeability of the core sample. Here you see the blue is showing the permeability of the sample before CO2 injection, and orange is showing the post CO2 injection. So we found for different samples for which we did the experiment, the permeability is reducing. Now what could be the reason behind this reduction? So for that we moved into further detail and we did some SEM analysis, and we found that there are some halide minerals that are getting precipitated in the core samples, which is resulting in a reduction in the permeability of those samples. Now, we tried to replicate it and understand what would be the case if we do the simulation, if we do the injection of CO2 for say 100 years. How is it going to behave? Are we going to see some precipitation? Is it going to affect the injectivity of those reservoirs? So we tried to do some simulation, which is basically we did the reactive transport modeling using Tough React, and we observed some changes in the gas saturation, some porosity, and pH. We observed that major changes that are happening, it is happening near the wellbore, but we could not see any sort of salt precipitation in them. Now, to understand what exactly is happening at the pore scale level, we moved on to the pore scale experiments. Now, as Hannah described, that why pore scale modeling or pore scale understanding is important, because it captures the fundamental physics of fluid flow. It helps us prepare a better model. It also helps us in assessing the risk because it gives us the measurement of properties such as wettability, capillary effects, and that would in turn help us understand the injectivity and also a better storage capacity estimation. This also supports the design optimization of CO2 sequestration. It also helps us understand the heterogeneity and anisotropy in the rock sample, and it in a way bridges the gap between the experiments and the numerical simulation. So for the experiments at the pore scale level, so the experiment design is as such. First is the rationale, followed by the objectives, followed by the design and planning, how we conduct the experiments, then what would be the methodology or the workflow that we are going to follow, followed by the analysis of the results that we would get, and finally, what would be the way forward. So as I described earlier, that we did some core scale experiments, we found that there is pore precipitation happening, and that is reducing the permeability. So that was the rationale to conduct these pore scale experiments. So the objective of the pore scale experiment was to investigate how CO2 and brine are interacting at the pore scale level, to understand what would be the optimal conditions at which salt precipitation might happen, and finally to develop and validate these simulations which are reflecting exactly what we have observed. So the experimental setup, we did the microfluidic experiments. So these are the microfluidic chips. These chips, we took two chips. One is of the homogeneous pore network, and the one which is at the bottom is the one with the heterogeneous network. This heterogeneous network is in a way reflecting the physical structure of a rock. So this is the core hole. This is the chip holder in which the chip is placed. This is a chip. These are the ferrules that we have used. And these are the experiments, the setup that we have used, where we utilize the oven and the microscope for observing it, pumps to inject the CO2, and that was the setup. So the process. First step was to prepare the brine solution. So for the brine solution, again, like we did in the core flooding experiments, we took the salinity of the Lithuanian reservoirs and prepared the brine solution with those salinities. So we did it at 120, 180, and to get, in order to understand that if salt precipitation might happen at a higher salinity and it's not happening at lower salinity, so we took another value which was a higher salinity, that's around 250. Then first step is the pre-experimental preparation. So this is the schematics, this is the whole setup or the design of the experiment, where we have this is the regulators that we have used. Initially, we used the CO2 pump directly connected to a regulator, and we directly connected it to the pore holder. Then later on, we moved on to the ISCO pump, which we used so that we could control the injection rate when we are injecting CO2 through it. Then next step was to system air flush. So that is the step where we inject CO2 through the chip so that there is no bubbles that are formed during brine injection. Then microscope observation. This we did both before and after both before and after injection, so as to understand what is happening in the pore network. Then finally, the last step after conducting all the experiment is the chipset cleaning. So for the chipset cleaning, we take after conducting all the experiments, we take the chips and we do the cyclic injection of distilled water and ethanol through them. We do 2 cycles of these, and then we keep these chips in the vacuum oven at around 60 degrees Celsius for around 4 to 5 hours, so that everything that's in them gets dried up and we can reuse those chips for another experiments. So this step, first what we did was in the experiment, we took the chip, we completely saturated it with the brine solution using the syringe pump. After saturating it with the brine solution, we injected CO2 through those chips, and then we kept those chips in the CO2 overnight. All the experiments, they were conducted at room temperature conditions. So we kept it overnight, and then the next day we observed the chip under microscope to see if there is precipitation happening. So these are the results of the brine injection, where above one is the pore network and below is okay, I'll just play so that you can see. Okay, so this is just showing how brine was, when we injected brine, how it was flowing through the chips. This is for the homogeneous network, that is for the heterogeneous network. The picture that is below, it is just showing highlighting the pore network from the chips. And you can see from the heterogeneous one that there are some isolated pores also. Obviously, those are isolated pores, so the fluid could not pass through them. So you can see those also. So the next step was the CO2 injection. So for the CO2 injection, okay. So this is the CO2 injection that is happening again in the heterogeneous and the homogeneous network. This chip is completely saturated with brine, and now CO2 is being injected through it. So it is showing that how the CO2 is trying to displace the brine. It gets dissolved initially, and then it tries to push the brine so that it could make some space for itself, and then how the CO2 is moving. So what we found was that there are some salt crystals after the experiment. We observed it under the microscope. So these are the images under the microscope that we observed. So we found that there are some crystals that that can be seen in the chips. Those crystals, they are majorly found at the inlet of the pore of the chip. All of them, they were found around the inlet, and there were you can see these salt crystals. There were salt crystals which were getting deposited at you can see here. Some of them got deposited around here. So deposition of the salt crystal around this location, which is the injection point, it is going to affect the injectivity of the samples. It is air, which obviously salt precipitation happens. It affects the injectivity of the reservoir, which in turn is going to affect the storage capacity of the reservoirs. So when we conduct experiments, we obviously have some challenges and some failures. So initially what we tried to do was, in order to observe the movement of CO2, we thought that we would use some dye which would be pH sensitive, and we could observe the flow of CO2 through it. But the dye that we used, it didn't dissolve properly, so we could see the accumulation of those dyes in the chip. So we had to clean the chip again and then reuse it. Another problem that we faced was during the system air flush, where we were trying to pass CO2 through the chip, but it got there was some brine solution that got it pushed back into the chip, and we again had to redo everything. We had to clean the chip again and dry it and do the experiment. So these were the failures or the challenges that we observed when we did some experiments initially. So the last step is the pore scale simulation. So idea was to actually understand how the pore scale was happening at the experimental level and try to replicate it at the simulation phase. So for the simulation, we used MRST, that is MATLAB Reservoir Simulation Toolbox. So the workflow of the simulation was like this. First is the porous map generation. What we did for the porous map generation was, we took the microscopic images of the chip samples. So we had some zoomed images of the sections of these pores. So we replicate, for the homogeneous one, we replicated it so that we could create a similar image of the chip. Similarly, for the heterogeneous one, those images that we took, they were randomly distributed so that we could get a heterogeneous network. The next was the color code mapping, where we assigned numbers because it doesn't understand the colors. So we assigned them numbers. We assigned zeros to the grains, and we assigned 1 to the pore network, so that 1 would be the one through which the fluid will flow. The next was the porosity and permeability map generation, where we gave the porosity and permeability values to those networks. Then the fluids and initial conditions were assigned. So we defined that injection is happening from one end and it is flowing through the other. So it is flowing from right to left side. So it's from W1 to W2. And finally, performed simulation. So where we defined the parameters of the reservoir of the chip, and we defined those values, and we tried to flow CO2 through them. So for the first, that we considered two cases. One was the uniform permeability case. So for the uniform permeability case, we did for both homogeneous and heterogeneous, and we could see that how the fluid is flowing, or the CO2 is flowing through homogeneous network and the heterogeneous network. But when we changed the permeability of the in the simulation, so we observed, what we did in this case was that permeability is increasing from this end to that end. So it's like from top to bottom, permeability is decreasing. So because you can see permeability is decreasing from top to bottom, the flow is somewhere going towards the top for both homogeneous and heterogeneous. Though for homogeneous, because it's a uniform network, the flow is more uniform as compared to the heterogeneous one. So we tried to match those results with the experiments that we have conducted, and we found that we were able to somewhere model the flow of CO2 through those networks. So on this side, these are the experimental results, and this is the simulation one, where we could somehow replicate how CO2 is flowing. So this is what we have done so far. So the next step would be to actually replicate exactly the salt precipitation that we saw in the experiments. So we have to understand that so that we could understand the pore scale level and of the chemical reactions that are happening. So we'll try, the next step would be to replicate the changes in the porosity and permeability by salt crystal, to assess the impact of the pressure variations. Because these experiments were conducted at ambient conditions, so we would try to do these experiments at high pressure and high temperature conditions, so that we could have different phases of CO2. We did at gaseous phase, so we would want to do it at supercritical phase as well, so that we can compare how CO2 is behaving at two different phases. So this work, I would like to acknowledge Harriet University, the DigiPortflow group, with whom we conducted these experiments, and Lithuanian Research Council, who's funding the research project that I'm working on. Thank you.
Thank you, Shruti. So I will start with the question that we have online. I'm just reading. Given the heterogeneity of Baltic saline aquifers, what level of confidence do we actually have in long-term plume migration modeling, especially considering cap rock integrity over countries?
What we are trying to do is that we have the core samples from the Lithuanian reservoirs. So we have even scanned those core samples. So we would be able to capture the exact heterogeneity of those core samples and understand how the pore network is for the Lithuanian reservoirs. So I think we would be able to do that after this, because we have these images. We have the scan images. We have the digital, like Hannah said, they have digital twins of those networks. So we can do the simulation and understand how it is working.
Certainly convincing to me, your presentation. Thank you.
Thank you so much.
More questions? Alex, not you this time. All right. Anna.
Can you go back to the MRST simulations? It's gone. Yeah, so in this, especially the bottom one, the homogeneous pore network, it's perfectly symmetrical, isn't it? So then how are you creating that instability? So it has to be a numerical instability. So I'm just really amazed that it's matching the experiment so well on the top versus the bottom.
Yeah, for this we have changed the permeability in the homogeneous network. So in this, the permeability at the top is higher compared to the permeability at the bottom. So that's why the fluid is flowing in that direction.
And you're imposing this as a boundary condition. You're not. It's not actually precipitating salt.
Yes, it's not. It's not.
Okay.
Yeah.
Okay. Yeah. It makes sense now.
Thank you for a very interesting presentation. I marked that you used 0.5 porosity, 50%. Did you try with more common porosity for our countries, something like 20% or 30 maximum?
Because we were doing we had the microchips which are 50% porous. So we were trying to replicate those experiments that's why we have used 50%. So later on, when we would try to model the salt precipitation, we would try to accommodate the actual porosity of the reservoirs.
Okay.
Thank you.
All right, if there's no more questions, then we will, thank you, Shruti.
Thank you.
We will complete this session with final speaker, Eugene Holubniak. The floor is yours.
Well, thank you for inviting me to speak. This is going to be a little bit change of gears a little bit, because this is going to be on a much larger scale, also a lot more complicated in terms of not in terms of scientific inquiries, but in terms of actually real life sort of problems that are not less messy. So this particular case that I'm going to talk about is my personal experience. I was involved in this heavily when I was at the Kansas Geological Survey. Kansas Geological Survey is basically it's a geological survey for the state of Kansas. In this case, one of the largest surveys in the country. How many of you know where Kansas is? Okay, good. At least there is some knowledge. So it's basically, imagine United States. It's almost at the geographic center of the United States, somewhere in that. Some argue that the geographic center is in Kansas. It might be true, might be not. We'll see. But basically, there is also a special injection program that was developed a long time ago for injecting different things in the subsurface. And this is what the abbreviation UIC, underground injection control, means. And this is kind of lessons learned from my experience dealing with Kansas problems of injecting different things into subsurface, basically. And so we're going to talk about the competition for the pore space. Because if we're injecting CO2, it will become very quickly very relevant, especially if you have other uses for the said pore space. And in Kansas, we do. In Kansas, there's plenty of uses for the pore space. And so who is competing for the pore space? This is what we kind of will try to understand. But kind of here's an outline for this competition, how I found out about the problem. So, you know, you're kind of, especially the younger you are, the more arrogant you are. Maybe I'm still arrogant, maybe it means I'm still young. But the thing is that the more arrogant you are, the harder you basically get hit, and the harder your understanding and your conclusions are kind of more lasting as to what might happen if you don't know the landscape. And then oftentimes you don't know landscape not because of your arrogance or ignorance, but because previously those problems didn't exist. And in this case, in this particular case, that's the problem. The problem didn't exist in the first place, but it is a problem today. And so I'm going to talk a little bit about our pilot CO2 injection at Wellington and the seismic array there. There are also additional complications to the problem because during that time, which was about 2010, 2013, 14, we started developing a new shale play. So unconventional oil and gas, where you do horizontal drilling and you pump water in, frack the rock and get a resource out. And in our particular case, this is the Mississippian lime. There is also Woodford shale. Both of them are sort of connected, or basically part of the same system or a similar system. And both of them are not particularly good oil and gas reservoirs. And then, they do have oil, and you can get it out, but as a additional prize, you get basically a lot of water. And the water cuts are, on average, 95%. So for every 5% of oil you get 95% of water as a prize. And so that makes them marginally profitable. Very, very poor profits, especially at that time, this new unconventional plays, and that both the Miss Lime and Woodford shale both are complicated reservoirs with complicated fracking systems, and there are vertical wells that perform better than horizontal. And how do you distinguish? Basically, it's a complicated play. I'm not going to go too much into detail. I ate a lot of that, and I can speak for hours about this. But the problem is that water, when you frack it, comes to the top, and you have to deal with this. And in order to deal with this, you cannot re-inject it into that Mississippian lime. So you have to inject it somewhere else. Where do you inject? Or maybe there are other uses for this water, but mainly company, because it's much cheaper. It's not free. It's much cheaper. You re-inject it in some other location. And in our case, it was on Arbuckle reservoirs, a vast, very large, 300 and more meters thick, beautiful carbonate that is basically an interface between that said Mississippian lime Woodford and the basement rocks. And that proximity to basement is something that is important to the story, because Unfortunately, when you inject this amount of rock and it's in proximity to basement, it is connected to basement and stimulates the basement, and that produces earthquakes. And then, of course, there are earthquakes. Earthquakes because we started using all of this water, injecting into our buckle, stimulating the basement. And it is proven, by the way, that at this case, it is an induced seismicity problem is originating from injecting water into this Arbuckle reservoir and stimulating basement. There is not much doubt about this, and the fracking itself does not cause the earthquakes. It is this dealing with the produced water and injecting it in the subsurface that's what causes. This is a cause of earthquakes. And so you have the kind of two users for the pore space, at least so far, and at least kind of on the face of it, is for this Arbuckle reservoir. So you have class 1 wells that are normally classified for municipal use, because municipalities use wastewater injection, for landfills, for also hazardous wells, things like OxyChem, for example, used to dispose chemicals into this, and large amounts of chemicals into a subsurface. And these kind of users compete with the class 2 wells, which is the oil and gas industry, basically dealing with the oil and gas outflow of water. So the reason they compete is very simple. It's because they're governed by different bodies of regulators. And so you have Kansas Corporate Commission handling regulations for oil and gas, and you have KDHE, which is Kansas Department of Health and Environment, dealing with the guys who inject from municipal landfills and chemical hazardous waste. Because they're governed differently and they're governed by different regulators, somehow they become sort of enemies, basically. And so that's kind of the premise for the war, for the competition. And then we're going to go into sort of similar case. And I'm not going to go into too much detail about this, but there is also already other signs of trouble. And they're as severe, if not more severe, than in the case of Kansas and Oklahoma. And this is in North Dakota. There's Moss River's Denbury case, where there is already a precedent of a direct lawsuit for the competition between the pore space users. And this is not related to CO2 use yet, but it is going back to that same kind of idea that we had in Kansas and Oklahoma, where two interests collide. We didn't have a lawsuit yet in Kansas that is directed at the pore space use in Kansas, but there is a lawsuits directed to earthquakes and the effects of the pore space use. And so it's a serious issue because it's a liabilities and risks, and investors don't usually go well together, especially if there's unknown in terms of how you handle those risks. So that's kind of why it is a relevant conversation. So let's talk a little bit more about geology, so that I'm covering different codes, and it's not just about law and regulation. So this is what we have in Kansas. This is a different geological maps of what we have in Kansas, and in this case we're targeting Arbuckle. So Arbuckle, although Kansas is as flat as pancake, scientifically proven, there's a paper on that basically is studying GIS flatness of Kansas. It is as flat as Kansas, although we are increasing the elevation towards Colorado, but even that still qualify as Kansas as flat as pancake. But subsurface is actually a lot more interesting. It is a lot more exciting because of reasons. So one of the reasons is that here we have a system that comes through all the way to Oklahoma, which is a rift system that used to pull apart continental North America, kind of ripping it apart, and the legacy of that system still lives there. It's very faulted system. There's also here is the uplift kind of in the middle, central Kansas uplift, as you see, and therefore the depths and the structure and faulting is very different depending of where you are in Kansas. That makes our environment where you inject different things into a subsurface non-uniform, and therefore this also complicates the story, because you can't provide a very concise picture if you have this kind of thing to regulators and to also to your sort of customers, to people who are fighting amongst each other. And that's what we had to do, me as one of the principal engineers on the Induced Seismicity Task Force, had to basically convey the story and kind of explain. And how we stumbled upon the problem, we actually, surprisingly, but also thankfully, saw the problem coming kind of far in advance. And the reason for that was the CO2 pilot that we had at that time going on, funded by Department of Energy. Because it's a CO2 pilot, and because it was early, sort of, mid-early days of CO2 sequestration sort of efforts and developments, we put everything in the kitchen sink at that field. We put seismic array, which will become relevant, and different sensors and fiber optics and all of those kind of things in there, just to kind of see what's going on, because we didn't know exactly what is going on if we do inject CO2. And we did inject CO2, and you see we brought in trucks, and the trucks, Lindy would bring in trucks, and it was cumbersome, yes, it was expensive, but again, no, early days, we didn't care about cost that much at that moment. We just needed to understand if it actually is going to work. And the CO2 actual pilot performed very well, and we were ready to inject CO2 in for the sequestration, for storage site, again here in Arbuckle. And that's why we were like, well, let's look into the seismic effects. That will be fun to study, and we had a seismic array there. And we were preparing for this exactly in about 2012, 2013, and this is exactly when the problem of induced seismicity started to come in. And we started seeing earthquakes in smaller numbers and also in smaller magnitudes way before we started seeing larger ones. And so we actually informed regulators about this, not to alert them, but basically said, look, here's a peculiar story. We have those earthquakes coming. Here's this seismic array, and it's one of those early warning, very small. You see 1.2 starting from 0.4 magnitudes coming in, and lots of them, and in specific locations. And we could basically see faults, and it was so fun, very very nice, very kind of revealing exercise for scientists to see, faults highlighting in the seismic. It was very, very nice exercise all in all. And then things started to change, because we started to get this activity from oil and gas people, and we basically started earthquakes, waves increasing, and also magnitudes increasing. And mind you that we do have we did look into the recorded earthquakes. There's about 30, maybe a little bit more, earthquakes that are recorded from early on, 1981 through 2010. So not that many, but again, we didn't have instruments and so on and so forth. But now we do, and then all of a sudden we started recording, not only seeing more earthquakes, but we also started to see sort of the results. One of the fun ones, if you can see, this is a NOAA site, and the radar picture where you see birds taking off during one of the larger events. You can see them on the radar, because we were monitoring so much. We watched the information basically as we go from different sources. But you could see one of those larger events that was 4.7 event. But we also saw 5.6 event in Oklahoma. I actually woke up, although my house in Lawrence was kind of almost 250 miles away from the epicenter. I still woke up because my house was shaking because of that earthquake. So basically, effects not only kind of recorded on your seismometers, but also some things that people started seeing, noticing, but also taking into account, because U.S. is a notoriously litigious society, and so people started getting notice and saying, "Well, look, there are cracks in my foundation, so I'll go and sue." But who is going to be my who's going to answer for this? Well, that was not clear. Here's the kind of the progression from about 2013. This is where the peak of the activity kind of started, and all the way to 18. And you can see that, we have a lot more, and basically starting from 14 to about 17, a lot more events than normal. And that's basically that. When we started seeing things collide, not only between sort of public and whoever, but also between the corporations. And when giants collide, this is not pretty. I was one of those caught in between those giants and the public, trying to answer questions. And the difference between those two is that class 1 and class 5 injected on sort of layman terms on vacuum. So basically, they had to inject without back pressure. They cannot pressurize the injection. So whatever goes into the well, it goes. And oil and gas had a privilege because they had 500 psi that they could put on top of their wellhead to make sure that actually they can inject more. And plus, because we were thinking about injecting CO2 in that specific region, here's also the class 6 EPA involved, because that would be us. And we were told at that moment is that, oh guys, you want to inject CO2 in this particular place? No way, nobody will allow you to do this because you already have the competition between those two. Here is a little bit, that was a bit, but basically here's the map of the wells. I'm not sure why it shifted, but blue are the oil and gas injection wells, and you see where the oil and gas sort of collides, and the larger the footprint of the bulb, the larger the injection is. And then you see, orange are class 1 wells that are chemical industry and municipal use. And then you have only about 49 class 1 wells, but you have a lot more, 2,381 wells that were injecting for oil and gas. And a lot of them basically coincided, and a lot of them definitely competed for the pore space because they started to get into each other's zone of influence. But why didn't we see this problem before? Because before those years, before 2013, nobody cared. You could inject ultimately the unlimited amount of material into a subsurface, but then all of a sudden, kind of the pore space ended. Why did it end? Well, because of this graph on the left, you see the volumes are increasing towards 2013 and peaking at about 2014-15. But this increase in volume was substantial enough to make the system non-elastic. It's no longer became infinite. It became very, very finite, and this is why the pressure started to increase, and that's why we started seeing this actual competitor, because all the pore space in there is connected. It's a carbonate system. There are fracture networks that are connected with each other, and then also they do stimulate. They go all the way into the basement because there's this rift system and so on and so forth. So it is a complicated story. But what it means is that all of a sudden, you were loading it at this much, and once you increase it twice from before, then you start seeing those effects. And here go the regulatory action. Will not go into too much details, but basically KCC, Kansas Corporate Commission, said we because there's more injection happening on the oil and gas side, we'll take action, we'll decrease the amount of the volumes, the water that you are able to inject in specific areas. And so they said, okay, only 5,000 barrels of water per day per well, and the maximum injection level of 25,000 barrels per day for wells outside of the area of concern. And so also there were wells that were injecting kind of together, so twin wells, we called them, no more twin wells, all of those kind of things changed. And so there was later all order kind of, we had several iterations of that to make sure that industry this has a chance to survive, if not survives. And then the second order would be, okay, let's actually make it even more strict and inject even less in certain areas and so on and so forth. Here's the map. You can see red dots are the earthquakes, and the yellow or orange ellipses are those areas, so, and the faults that we identified around which you should inject less. And actually, it seems to be it worked. It worked for two reasons. It's not only the KCC order, but also it's the shale play was not as economic as people thought it would, and so you see decreased activity, but also decreased activity in terms of earthquakes. That's kind of the end of the story. And so for that, legal network and regulatory network framework for the state of Kansas. So for the CO2, specific to CO2, the reason I'm talking about this is because even before CO2 could be injected, there was already a problem, and we'll see those more and more of those problems moving forward. That's why legal and regulatory network is essential in this case. Basically, governing who owns the CO2, who is responsible, whose liabilities these are, and making sure that there is understanding of what to do moving forward will de-risk the situation quite dramatically. And so for the Kansas, it still remains the way it is, the way it used to be. Although at the moment there's a huge movement from ethanol producers, from oil and gas, from the multiple other users to change whatever we have, especially related to CO2 storage and sequestration. And so basically the pore space issues still need to be addressed, and they are being addressed at the moment. And there are ways to eradicate those problems. There are experiences from CO2 EOR, CO2 enhanced oil recovery. But again, every state in the union addresses issues differently. There is a pathway for Kansas, but if we're speaking about Baltic region, I'm pretty sure you will have kind of similar issues moving forward. There are also definitions that exist for different spaces. That's what makes United States so fun, but also complicated, and some people want to pull their hair out, especially me as a developer. Knowing those issues both is beneficial, but also it's a big brain drain for me. Started forgetting things. But basically, if you go into different states that do inject water in the subsurface, there are issues related to who owns the pore space, whose liability it is, what happens if things go south, and these are things that are still kind of in the process of being addressed. And again, the reason it is important to be addressed, it's that the lawsuits would be a little bit easier to solve and a little bit more clear, and maybe avoided in the first place because we know the boundaries and so on and so forth. At the moment, this case kind of is basically was decided in the favor of whoever owns the mineral space. So developer lost in this case, and so in order to avoid that, we need to know our operational boundaries and operational activities that we have. So that work was both Kansas Geological Survey plus the Department of Energy sponsored way long time ago. If you have any questions, I'll gladly take it.
Thank you. Very concerning, Alex.
Okay, that was extremely interesting. I'm glad that fracking is banned in Europe, to be honest, to start with. But, well, do you think, I mean, again, I'm not a geologist, but from your experience, would you also comment perhaps on the issues of contamination of water aquifers? Because you mentioned seismicity, right, and earthquakes, but as far as I know, at least in Europe, when the first studies were conducted, people were also, those involved in the process were also claiming that there's a water contamination issue. And also because of that, I think fracking was banned in Europe. In case we inject CO2 and keep injecting CO2 because of the CCS activities, do you think there's a threat to basically similar problems could result because of that? Or
long, complicated answer. So I am not glad that fracking is banned in Europe, but again, I think everything should be weighted in case by case. I don't like the blanket solutions because it hurts more than does good. No matter that the problem is messy, you can solve it, especially if you have a cool brain. You can still address it, especially if you're methodical in your address. In terms of water contamination and issues of CO2, are they possible? Yes, we have a case today where ADM injected CO2 in a subsurface, and the leakage is so severe that they did damage one of the aquifers. It is the case today. We could talk about that in more detail. There's some articles that you can read about this. Again, is it necessary that every operator should be like that? No. I know ADM personally. I believe they were reckless in what they did. At the same time, it provides a case study and kind of lessons learned. At the same time, when I worked in a survey, doing survey work, we saw leakage from both oil and gas, but also natural as well. And sometimes things in subsurface change. You have different processes that are happening. And I did personally see a natural leak and also a contamination leak. Other concerns, other concerns for CCS industry, the same as to any industry. I don't believe we can solve our problems as humanity without actually pushing those boundaries and actually addressing the problems that we created. It's just not possible, not feasible.
There are a couple of questions online, if I can take that. Well, there are a few philosophical ones, but there is like one technical question. So it says that what technical uncertainties in pore space characterization, like pressure interference between well or cap rock integrity, proved hardest to model?
So actually, in our case, cap rock was not affected by whatsoever. It's just a different system. And again, we discussed with Ala and Hasbulla beforehand that geology is very interesting topic to study because systems are different everywhere. They're not uniform, and whatever is happening in Kansas is not happening even across the border in Oklahoma is already different. Although it shouldn't end at the border, but it coincides with the differences in basement because Anadarko Basin kind of dives deep into Oklahoma, and so in Kansas it's super shallow, and in Oklahoma all of a sudden it becomes very deep. Anyway, and so the systems that we govern in there they also become very different and so on and so forth. In our case, the boundary of concern was not the cap rock, but it was actually the basement, because all of the water that was injected, and it's still being injected in Kansas, I believe actually is pushing the pressure, not because pushing it up that doesn't make any difference, doesn't make any sense, but it does spill and stimulates the basement more, and that's why we see the earthquakes. I mean, that's kind of makes sense.
Okay, I do have one question of myself. Okay, so you showed this in induced seismicity, and I think these phenomena are also documented in other places. For example, NAM in Holland is an example of that. But typically, a responsible operator will operate fields based on what is known as voidage balance. Whatever comes out, something needs to go in to replace that. So that's a standard practice. And it's also monitored in many, at least the responsible operators that I know of, they have classical plots of voidage balance in the different areas. And you're saying, you're nodding your head, it doesn't happen, but it seems like an issue more from the operational side of things rather from, and it was the same case in NAM. The NAM operator wanted to produce as much gas as possible, as fast as possible, because the gas price was high, so they can make more money on it. So these kind of things are more kind of irresponsible operations rather than actually okay.
100% yes. So in order to say, well, responsible operator, it's kind of like the joke about spherical horse in vacuum. Responsible operator is the same as spherical horse in vacuum. It doesn't exist. I never seen one. There are good operators. There are a little bit more malicious, but the best never is there. And so theoretically, yes, there should be that balance and so on and so forth, but it doesn't exist, unfortunately, especially when you're dealing with this amount of fluid, and if you're dealing with the tight formation, you cannot return anything in a tight formation. Nothing will come to a tight formation. You will not be able to inject, and that's why you see this in Texas, you see this in Alberta, you see this in Marcellus, multiple places today they experience this because they cannot inject in tight formation. That's just.
Okay, thank you, Eugene, for a very nice overview. We are a little bit ahead of our schedule, so but we can take the coffee break now, 20 minutes, and there is also there's time for some posters at the back. So if you guys have some questions, I mean, you can spend some time. So maybe we'll take 30 minutes for the coffee break. In that time, you can have your coffee and also discussion around the posters at the back. We'll come back at 11:10, and then we can resume the session. And maybe this will gain us some time. And during the lunch break, maybe some people want to check out, so they can use that extra time for the checkouts and all. Okay. Enjoy the coffee and the discussion around the poster.
the last session today. It is case studies from regions and countries. And the first presenter is Mai Uibu. She is senior researcher at the Laboratory of Inorganic Research in Tallinn University of Technology. She also program manager for Chemical Materials Energy Technology doctoral program in the Engineering School of Sciences in Baltic. She defense PhD in 2008 on CO2 carbonation. I remember I presented at that time. She was very young, and it was very nice defense. And so also Mai is a laboratory test coordinator at Ragn-Sells for oil shale ash service. The presentation the company which presented yesterday for us. So she is responsible for this technology from Baltic, because technology which Ragn-Sells presented yesterday, it was developed in this laboratory by Mai, her supervisor, Rein Kuzik. Unfortunately, we lost him this year. And Mai, the floor is yours.
Thank you, Alla. Very nice to go down to memory lane. It just shows how long we all know each other. Anyway, yeah, just to introduce myself maybe a bit more that, yeah, I'm Mai Uibu. I'm here as a Ragn-Sells representative, but as most of the work still takes place in the laboratory in Tallinn University of Technology, then with all these my people from my group, also doctoral students, then I'm presenting from both of us. So the talk is gonna be about CCU, reclaiming mining and industrial waste for use in green building and metal recovery. A bit of the layout of the team. First, I'm gonna introduce a project that tackles both of these issues. This is TEMTA 87. I'm gonna introduce the objectives a bit. Then I go more into the waste-based and carbonate-based building materials that are developed in the lines of that. Then more specifically into OSA project that is deposited oil shale ash as a raw material for precipitated calcium carbonate, but not only. A bit of the main challenges and of course thanking everyone. So TEMTA 87, this is this is a project funded by European Union and also Estonia. It's a complex recovery of mineral mining and industrial waste as secondary raw material in the context of building materials and also hydrometallurgy. So the main concept is that how to say, landfills from the past should become the resources for future. So instead of opening new mines, use the old landfills. What is usable from them? So there are two, I would say, directions in this project. It mainly deals with the big oil shale ash mountains in eastern Estonia. First of all, valorizing them as a low-weight building materials using mineral carbonation approach. And the other, which is more connected to OSA project, is to valorize it in the context of hydrometallurgical methods. First, OSA project takes out the calcium to produce calcium carbonate, And then the residues should be maybe considered as a magnesium resource or some other elements to achieve like waste-free and everything used up maximally. So going further, waste-based and carbonate-based building materials. What are they? Why they're good? First of all, there is a big trend in utilizing more waste flows in building materials. First of all, of course, we don't have to use that much virgin resources. Otherwise, also, we reduce the waste flows. One of the techniques that can be used for that is carbonation, which also reduces the carbon footprint of building materials, which is, as we know, very big from cement production. And for that, we can use direct carbonation, but also use carbonated materials as fillers in these materials. So to go forward, the main motivation is comes from oil shale. Of course, some time ago, oil shale was considered like the greatest resource of Estonia. Of course, now it's more like the greatest villain as a fossil fuel, and it's is currently used as well, but the future is quite unsure. However, it has left us with a great legacy from decades of using not only the CO2 in the air, but also the ash mountains. Estimated 600 million tons of landfill ash, which contains, as you can see, these quite common materials known in building materials. But of course, as they are already deposited and stayed in weather conditions, they can't be directly used as binders in building materials. So something has to be done with them. And the other goal, what is to use to activate the landfill ash, is also maybe underutilized resources in Estonia. It's this illite containing low quality clays, and we try to combine it with the landfill ashes to produce better building materials. So yeah, the main objectives are to assess all the raw materials that we want to use, mainly landfill oil shale ash, but also clays in the view of its pozzolanic reactivity, also the ways to activate them through mechanochemical and thermal activation methods, also the effect of co-calcinating them both, to achieve these cement blends, and as further step already to produce these lightweight building blocks using accelerated carbonation curing. And finally assess landfill ash as a cement replacement in building materials industry. So to go more into detail, we actually investigate 3 different clays from Estonia, from Aseri, Arumetsa and Punda, and also landfill ash. And how it looks like, this is the clay, how it first comes. It has to be dried, it has to be milled and grinded in different equipment. This is actually a quite important step, but also energy intensive step. And and later it's thermally activated through heating at different temperatures, which seem high from 750 to 900, but as compared to the conventional temperature used in cement production, they are still considerably lower. And as said, next comes the assessment of pozzolanic activities. For that, according to standard, we produce these blocks. And the results showed that actually using these low quality lithic clays, the minimal pozzolanic activity requirements is well achieved, and they could be considered using in combination with landfill oil shell ash. So next, the experiments led to co-calcination of landfill ash and also dolomite as, this model mineral in combination with clays at different temperatures, and performing isothermal calorimetry analysis for them. And as we can say, so far, the results look promising. Of course, the performance assessment has to follow to, confirm our expectations in the like to get enough strength, durability, environmental friendliness, and so on. So moving on to these cellular blocks or lightweight blocks, in this image, it's basically shown how the doctoral students are making them. First, they're mixed. As in these tests, the landfill ash is not activated yet. We use two different ones. The initial landfill ash, which is just dried and grinded, but also carbonated landfill ash mixed with Portland cement, aluminum powder to get these bubbles, water, and in some cases plasticizer. Then they are mixed, casted into forms, and the molded samples after 24 hours look like this. And then they're inserted into carbonation chamber, and they're treated with CO2 or with flue gas. And to final testing for strength, density, environmental stability goes these little cubes. So actually, the results show that if we just take the not activated landfill ash, we can use up to 20%. We can put instead of into cement 20% of this landfill ash as a pillar to achieve acceptable results. What is good thing that in the process, CO2 uptake is 10 to 15%, which makes this technology quite attractive. Of course, the work continues in order to activate the landfill ash together with clays to achieve more uniform results and also to achieve, I would say, more applicability for this landfill ash. Because low weight bricks, they can be used in some cases, like inside buildings, but there is a possibility to get as strong as real cement using landfill ash. So moving on to The other direction, landfill oil shell ash as a raw material for precipitated calcium carbonate technology. So on this picture, we have actually drill cores from the ash mountain. This is how they more or less look like. Some parts are softer, some are more hard. Also depends on the technology that was used for oil shell combustion, like in the previous times, pulverized firing was used. Nowadays, it's more oil ashes and also circulated fluidous bed combustion ashes, which means the ash composition is a bit different mineralogically, and it also affects the deposits, of course. However, studies, a lot of drillings have confirmed that actually the usable calcium inside the ash is quite comparable with the fresh oil shell ash. So 10 to 30% we can leach out quite easily using ammonium solvents. The main process is here. So the landfill ash first is extracted, calcium of it using ammonium solvents, and then using simple carbonation bubbling, we get PCC, and inside we sequestrate the CO2. Then from extraction we get residue, which can actually quite nicely be used as a fertilizer and also as some kind of filler. But if we consider bigger production, then maybe more applications and more research should be required. So this is the development of secondary process and maybe getting out of that some critical raw materials as well. Here we can also see the different kinds of PCC that can be produced using the technology by varying the operation conditions. We get many different sizes, different morphologies for different applications. So this is really exciting. And another thing is that the process itself is very selective towards calcium, and the PCC that we get is very pure. So what started in, of course, previous studies went on for decades, but more like cooperation with dragon cells started 2020. See, then after the first results and patenting, what started was then, how to say, Northern Europe's largest circular economy project involving these ashes. I think Kalar Saluste yesterday already covered more general parts of this project. So the aim is to produce calcium carbonate, to produce it, how to say, CO2 negatively, use it should be waste-based, also zero liquid discharge, so no wastes out of it. And the top of all, it should be also economically viable. So the demo plant that is now opening soon should give some answers for that. So coming back to this raw material crisis, it is actually getting more serious year by year, which is also represented by the EU classified chemical elements that year by year, they list more. And one of them is also magnesium. That seems to be a very common element actually, but the market is like that all of it is produced actually in China, who runs the market. So one of the solutions would be also to use these secondary products of production or waste hills to see the composition and if some of it is usable in the context of producing some of these critical elements as well. Actually, as the natural resources are depleting, sometimes the landfills can contain more in higher concentrations of these elements. However, in oil shale ash, the concentration is low, but as the material is already being processed and pre-treated, then there might be ways to run it also economically. So this is how it started in 2020 with these small reactors. In 2024, we had the demo plant on paper, and now the building is ready, and soon the equipment will go in. And by spring, we should have the demo plant to start testing landfill oil shale ash for PCC production. But the development doesn't stop there. In laboratories, we continued testing, also to extract magnesium, maybe iron. Also, we have tried to produce amorphous nano CO2 from the residues. So here actually is the composition of the residue of PCC process from landfill ash. And we had treated it in using several inorganic, organic acids, different concentrations to get the process as environmentally benign as possible. And as one of the products, we have extracted magnesium hydroxide, actually, also in quite pure form. Also, nano CO2. These are actually, like, the processes itself are known, but to find the correct one for your waste, this is more difficult. Also to get it the way that is worth using in industry or commercially. So, yeah, and this is actually the one of the last slides, just to remind also that there are challenges. First of all, that the regulatory ways for how the CO2 bound into these materials in situ are calculated, especially is it like a permanent storage or not, or how long is considered a permanent storage, so it can be used also as to benefit your product. And the other thing is that although it might seem that there is like inevitable amount of these ashes, when you try to get access or buy it, it might still be difficult. And then I want to thank
thank you very much. I have one comment that when we started to cooperate with Rain Kusik and with Mai, somewhere 2007, 2008, so the role of CO2 use was relatively small compared to CCS in the climate change mitigation. So 5 to 8%. Then it's increased 8 to 10%. Now the prospects to increase role of CO2 use up to 30, 50, 60% by 2050. So, also Lithuanian government announced in their national energy plan that they would like to be hub for CO2 use products, and not only to use their own CO2, but to import CO2 from other countries. And I have a question to Mai. Of course, for this pilot first demonstration, what ash you will use? Mainly fresh, yes or no? No? What? Only landfill. No fresh anymore.
Is not actually allowed. If you want to get some money from government or in projects, so no fossil related material is allowed to use. So if it's already put into the landfill ash, then it's okay. So of course, yeah, it's gonna use the landfill ash, and yeah, as compared to fresh ash, much more difficult to
It is great.
handle.
It's news for me because when we worked in common projects, then we investigated fresh ash. And so the question, you reported 40 hills. Are these 40 hills are all available for using? Because I know that some of hills are recultivated, used for tourists, for sports.
I think here are considered all of them, but there is a lot of them are, of course, the main part belongs to Enefit, but VKG also have some hills, some are in private ownership, so there are actually quite selection. If you can't like agree with on price with one, you can go to another.
Thank you very much. Any additional questions?
Thank you. That was very interesting to learn. My question, you referred to economic feasibility. Would projects like this always have to be funded by the government, or no? I mean, that's a very straightforward question because I'm trying to understand whether it will be beneficial for companies, let's say, to reduce the volume of waste so that they can economize. So will the support of the government be necessary always, or at some point you believe that it will be, economically self-sufficient, let's say?
Actually, this OSA project is mainly funded by Ragn-Sells. Of course, they have used some possibilities out there to get some money outside as well, but mainly it's their risk and their development. And of course, we hope that it's going to be viable. If the main help might come from this CO2 regulations, if this can be beneficial to make the project, the product more valuable.
Thank you very much. We have also questions online.
So there is one question online. There are a couple of them, but I think one which seems to be most relevant. From Dr. Sato, he's asking, what standard do these blocks meet, and does using different type of clay makes a difference?
First of all, the standards are quite, I would say, wide for the ones that use waste inside, but we are not aiming very high. These lightweight blocks, they don't have to be very, very strong. But they do have to be light. And of course, environmentally tested. And this still goes on. So right now, this is mainly laboratory phase, and we haven't made like maybe the right size blocks that could be tested for all the standards. Otherwise, of course, the clay makes all the difference. And these clays that we are testing are, of course, not the best. We are trying to use the locally available ones, and maybe the ones that are underused, because of course very high quality clays are also very expensive to get, like cheaper, more available uses as well.
Thank you very much, May. We will move to the next presentation. Uh, the next presentation will be made by Kazbulat Shagenov. I know him even longer than my, starting from when he was here. Before he was born. Yes, because he is my son, but I also his supervisor, and we're working together in research and development. Kazbulat is researcher in Tallinn University Technology. He is founder and CEO of Shogun Energy Consulting Company. He defends PhD on CO2 storage in Latvia and modeling in 2015. And he also he is working with educational carbon neutral technologies courses, which we give to the different stakeholders. Also, we make not only research courses, but we have project funded by Erasmus Plus, which is educational. We already made such project on CCS and circular economy. Online courses are available. Now we are working on the course on hydrogen full chain. Also courses will be available. So the floor is to Kazbulat.
Thank you. In the beginning, I would like to mention again about yesterday legendary day for us, for pioneers of CCUS in Latvia, in the Baltics. It's a special day. And we have been moving towards this day with everything we had, with dozens of research projects, with dozens of scientific publications, with courses we made for students, for industry, for policymakers. And this is our, let's say, victory. For about 20 long years, we promoted that Latvia is the best place for CO2 storage in the region, in the Baltics, even in Eastern Europe. And sometimes we stopped belief in this day that we will meet it, and were demotivated sometimes, but continued hard working with discipline. And this shows that discipline gives results. And I would like to thank everyone who participated in this journey. Baltic Carbon Forum, all participants, all member of boards, Pasrek CCS, and all institutions and companies who participated, Latvenergo, Akema, Schwenk, everyone. So this is our joint victory. And in the end of this emotional introduction, I would like to say that Lithuanians, we love you too. As said in the beginning, guy from Lithuania, don't give up. And I hope that we will, all together, we will move a situation in Lithuania the same as in Latvia. Altogether we are power. Don't give up. Thank you. And the last one, because we have here our friends and partners from the United States, I will. My today slogan is "Let's make CCUS in Baltics great." Not again because it wasn't before, but great. Okay, so let's start with my presentation. So today I will present recent results of techno-economic CCUS modeling for the Baltic offshore cross-border scenario using direct injection from ships. I presented it last year, but it was just first result of our scenario, and now we just received a very, very fresh results of our modeling. So CTS project, supervised by Norway, technical part of this ship's development is done by Nemo Maritime, and with support with Total Energies, Breivik, Schlumberger, OMV, and supported by Estonian Ministry of Climate in the frames of CETP Joint Call European project. And in this project, we participate with Shog Energy company. So some words about this concept. I'm not from this part of the project, Nemo developing this site, but I just say some words about the concept. So we can transport, capture and transport CO2 to the ships and transport it directly to the offshore storage sites connected to the infrastructure on the bottom of the sea floor, and we directly inject it to the storage site. So we don't need a rig. And so some words about technical parameters. So we will have big tanks on the ships with capacity up to 100,000 tons, but it depends on the on the needs and design. Some properties: pressure about 15 bars and temperature minus 28 Celsius degrees. And the ship will be equipped with onboard process unit for CO2 conditioning and injection pumps. So here you can see the cartoons. How does it work? So a ship will come to the storage site location, will connect with fuels and inject by pipelines or tubes to the storage site. So within the CTS project, we are focusing on 4 regions offshore: North Sea, Baltic Sea, Black Sea, and Portuguese Atlantic coast. We are responsible for the Baltic part. So our motivation in 2022, we produced in 3 Baltic countries about 15 million tons of CO2. And as we know that Estonia out of conditions for CO2 storage due to shallow sedimentary basin, and in Lithuania until now CCS is banned, and according just yesterday news, we have approved CCS in Latvia by Latvian government, thanks to them. And according to our previous studies, we found that Latvia one of the best in the region, as I said, with a number of very good onshore geological structures. And offshore structure E6 was estimated in my doctoral thesis as one of the biggest offshore and one of the prospective, due to not only the size, but very interesting special case, very interesting design. I will little bit briefly tell you about it again every time I speak about it. But anyway, now it is a really good time to repeat, because we just spoke with our partner, owner of the license, and we together with our US partners, and maybe it will be really good to repeat. So the distance from the shore is 30 kilometers, and structure split by inner fold into 2 compartments. Why it is important that we can use different compartments for different cases. For example, E6A, I call this this bigger part A for CO2 storage, and E6B for example, for hydrogen storage or other type of energy storage. So the structure quite big, 600 square kilometers. E6A is 550 kilometers, and E6B about 50 kilometers, and the depth is more than 800 meters. Temperature 36 Celsius degree. Good porosity within the Cambrian sandstone Damiana formation, 21%, and permeability 170 millidarcy. So we estimated storage capacity with different levels of reliability, and in average, it's of the biggest part, storage capacity is 365 million of tons, Also, we estimated on the top of this reservoir, we have artificial oil reservoir, 10 meters thick, where oil exists and could be produced. So it's a really special case where it is possible to make oil recovery and maybe enhanced oil recovery. And at the same time, in another reservoir, in another structure, in another layer, it's possible to store CO2 or hydrogen. So it could be. So I have another studies where we use this structure as a synergy concept. So let's go to our techno-economical modeling. So we used techno-economic analysis tool for regional CO2 capture, transport, use, and storage scenarios from Nermoen et al. 2022. This tool gives opportunity to evaluate different parts, capture, transport, utilization, storage separately and interconnected with different timings. So don't ask me about this monster. This is just example, but we have the same for our region. So every unit has own option, own type of so it is hub utilization or storage unit and interconnected, and we input different timings, what will be first and how it will continue in time. So methodology and assumptions. We are estimating technical costs, contractual, operational, and capital costs. We don't estimate risk premiums. Numbers shown are the cost of storage of 1 ton of CO2 avoided. Inflation used is 4% and discount rate is 5%, and electricity price is 87 euro per megawatt hour. And of course it could be changed and during times, but until now it is like this. So we considered 3 clusters according to countries: Estonian, Latvian, and Latvian-Lithuanian, and presence of emitters. We selected the largest emitters in 3 countries, located closer to ports. In some cases, not too close, but anyway. So first Estonian cluster consists of 2 subclusters. The first one consists of 5 emitters. 2 from Auvere, 2 from VKG power plants, and 1 from Kivili chemical plant. And CO2 will be captured in these plants and sent by pipelines to the Sillamäe port. And by ships will be sent directly to E6 structure, about 750 kilometers. And a second subcluster consists of 3 emitters: Horizon Paper Factory, Utilities Tallinn, and Iru Waste to Energy Plant. This is a place where we have been yesterday, very close located. And by pipelines will be sent to Muuga port, and by ships will be transported 500 and something kilometers to E6 structure. Altogether, Estonian CO2 emissions in this scenario is considered 3.9 millions of tons. In Latvian cluster, we have only 2 emitters and 1 subcluster from Latvenergo will be captured and sent to Riga port by pipelines, and by ships 400 kilometers to the E6 structure. And the biggest Latvian-Lithuanian cluster consists of 4 subclusters: Green Klaipėda, Waste to Energy. You don't see my mouse, yeah? Okay, sorry. Orlen and Akmenės Cement. It's number 5 on this cartoon. And Švenk Latvia, number 6, and Akema and Uebek Kauna Waste to Energy in number 7. All together will be sent by pipelines to the port of Klaipėda, and then 90.5 kilometers by ships to E6 structure. Altogether, we considered 16 emitters in 3 countries, produced 9.4 million of tons in 2023. In our model, we considered that capture will be started in 2031 in Akmenės Cement and Švenk, Latvia, and with vast majority of emitters joining in 2035. But rest of factories will join only in 2040, according to readiness level. We considered efficiency of capture 95%, and we estimated that it will be captured 353 million of tons over its operational period of 2031-2065, and 280 million of tons will be avoided. Technical costs of capture per ton vary significantly, from 20 to 30 euro for waste incinerators, and from 140 to 150 euro for some power plant, for some facilities for energy production. And here you can see costs for capture, corrected for inflation 200 euro and discounted 85. Transport in our modeling consists of 16 pipelines connecting 4 ports and 4 shipping routes. Total length a little bit more than 2,000 kilometers. And shipping routes can be further optimized, of course, but until now, so we have estimated, we used input 30 euro per ton for CO2 transported using a traditional method scenario. And for storage, in traditional scenario, we used a price of 8 euro per ton of CO2 stored, and in the model we input that platform need to be built, and drilling of 8 wells, and based on monitoring, of course, and total price will be 680 million euro. And abandonment and post-monitoring costs about 75 million euro. Well maintenance operational monitoring costs 31 million euros per year, and energy costs approximately 1.2 billion euro for heating and injection of CO2 for all the period. So overall, for Baltic scenario in traditional modeling is for 1 ton of CO2 123 euro per ton CO2 avoided, and total cost of the project 34.4 billion of euro, considering 280 million of tons avoided. Benefits of direct ship injection, so it's flexibility in delivery and optimization of routes. Dark ships may be a way to reduce emissions caused by being designed for less pure CO2, and can utilize cleaner fuels or onboard capture systems. No need for power production or electrification from the shore, while the energy requirements to heat and inject is the same, but ship engines can be equipped with CO2 capture or run on LNG ammonia to reduce associated emissions of CO2. Here you can see comparison of traditional and direct injection from the ship's scenarios for injection. So you can see that in traditional we have 8 euro per ton, and in direct injection 2.5. So it's savings of 30%, even a little bit more. For transport, in traditional scenario, it's 30 euro per ton, and in a direct injection, a little bit more expensive, 10% from the traditional 33 euro. But together, transport and storage in a direct injection case is 6.5% cheaper, 35.5 in contrast with 38 in traditional scenario. And general total comparison in this slide, you can see that the benefit is 2 euro per ton of CO2 avoided will be in a direct ship injection, and considering 280 million of tons for all the period, it will be not big difference, but still 560 million euro. I will not repeat conclusions because just spoke about it. Just in the end, I can tell that flexibility in delivery and optimization of routes will provide additional benefits, not only financial ones. For example, avoiding regulatory challenges with governments and environmental impacts, etc. So I would like to thank Ministry of Climate of Estonia and the CTP Joint Call European Union project. Thank you for your attention. If you have any questions, according to the ships, maybe I cannot answer in details because I'm not involved in this part. But according to the scenario, please ask any questions. Thank you.
Okay, thank you. I only want to add that in the CTS project, it is the most complicated scenario because it includes 4 ports, 3 countries, many emissions, and we will need not 1 ship, but in this scenario 6 ships.
We're using 6 ships?
6 ships, yes. Therefore, it is savings is not such huge. So the colleagues who already made modeling for 1 port, less ships, because we are losing on more expensive ships. If you have 1 port and less ships, then savings are more, of course. So it depends on your arrangements. So please, questions.
And also it's very, very case specific because it depends on distances from the ports to the storage site and distances, location of pipe, location of emitters to ports. So many factors that plays.
Do we have questions?
Thank you. Very interesting. Could you please comment on the geological structure that you referred to, when you said that you can theoretically store both CO2 and hydrogen? I'm asking this question because I've worked with some companies developing hydrogen storage options in onshore, not offshore, storage options in Europe. And let's say the Germans and French are primarily looking at salt caverns as the most suitable geological option. But some countries simply don't have enough salt caverns or may not have any at all. And they would then use the next best option, which is depleted hydrocarbon fields. And let's say there's a company in Austria that has already pioneered that, but it's only one company. Which type of geological formation you were referring to? Is it like depleted fields, or maybe maybe I just missed it?
It can be considered both. So we can consider the depleted oil, but until now it's not depleted. It's productive layer. That's why it's very specific. Maybe in the end of production, because until now we are not sure about the volume of oil in E6, but I hope that we will explore soon. So we consider it in the same sandstone, but another level. So it will be it will have falls, and it will be covered with from all sides in this E6B, and another type, it could be after the production of oil, it could be stored also in oil level after the production.
But I think that when we think about capacity, which we already know, it is Salina Aquifera, Cambrian, E6b in Cambrian part, because you see that E6b, we have numbers for capacities for E6b.
Yeah, so
yes,
it is
in
10
Cambrian,
millions
Salina Aquifera.
of tons
And
of
this
CO2.
capacity estimated for CO2 storage, but it will be enough for hydrogen. The idea of synergy scenario of Kazbulat to make production of hydrogen also offshore and to use saline water. And I've heard one presentation from Italian chemical engineers that production of hydrogen from saline water is needs less energy than from pure water.
You can check
It will
our
be cheaper
latest
price.
studies. We have it is not scope of this study, but you can find very beautiful circular economy concept where we have different type of technologies, storage, production, and so you can find it interesting. And we see that already some projects using this type of scenarios.
Thanks, Kazbulat. Very nice overview. There is one question online. Professor Kotak, he's asking how will this technology become economically feasible? Because as far as I can see, it seems like it's a very cost-intensive process, and I've not seen anything that makes it seem worthwhile. I mean, and I kind of agree, because the cost of the project you mentioned was like $34 billion.
Yes.
That's pretty expensive.
But during 35 years, so it is, and anyway, it's cheaper than traditional for €1 million per month. So, and in the beginning, of course, technology is expensive, but during the development, of course, it will be cheaper and cheaper. And now we're just developing this technology in the project, and we need to build a new ships. But later, it will be upscaled, and of course, price will go down. It's always with new technologies like this.
Okay, thank you.
Just to add to question, because I'm cost, I can also. It is all the cost for 35 years for all the project. It is not capital cost which is needed at the beginning of the project. Operational cost, for example, for capture plants, higher than capital cost. And it is for 35 years period for many plants included, altogether. So. For what unit cost? Yes, one average 120. Yes, yes, but of course the highest price is for capture, as usually. So we have the last speaker today, Alexandra Dodo. But after this session, of course, we will have also panel discussion. Yeah, yeah. But now the last speaker in this session, Alexandra Dodo. Alexandra is leading CO2 geological storage department in Geokamar, Romania, and she was graduated as geophysicist with master on geology and PhD in geology. So she is involved in many activities on CO2 geological storage, national, international projects. We worked together with Alexandra in different EU projects, maybe during 20 years. A little bit.
Starting with 2008, when I started working in Geokamar and in CO2 geological storage.
Yes, it's a little bit less, but in 2 years will be 20. In 3 years. Okay, and Alexander was 2 years previous president of the ENERG network during 2 years. It's energy network for energy, European network for research in geoenergy. And okay, she will tell us a story about Romania, please.
Thank you very much, Ala, and thank you very much for inviting me to present. Thank you, Mayur and the organizing committee, and congratulations for lifting the ban in Latvia. Hopefully it will be in Lithuania also. So I'm here to tell you a story of CCS activities in Romania, a high-level overview of this. I have listed here also my team on CO2 geological storage from GeoEcomar. Okay, so we didn't have a ban on CO2 geological storage, not onshore, not offshore. So we always had good premises for implementing CCS in Romania. We had industrial emitters, we had carbon pricing under EU ETS, and we had potential for CO2 storage onshore, offshore. And also we have implemented, as you will see at later slides, the CCS directive. Recently, we have high obligations under Net Zero Industry Act that could be a good incentive for implementing CO2 geological storage. And on my research part, we have more than 20 years in the research for CO2 geological storage, and we have also partners from Romania doing research on CO2 capture. Maybe you don't know, but Romania is one of the oldest oil and gas producers in the world. I forgot to mention this, more than 160 years of oil and gas industry. But starting with the premises for CCS, I will show the emission part of the premises. And here we have the industrial emissions. I must mention that the total industrial emissions verified for 2023 are only 23.84 megatons of CO2. On this map, you will see only the major emitters. The emitters that are have emitted more than 100 kilotons of CO2 in 2023. As you may notice from this map, or I don't know if you see very well, the larger emitters are actually the coal-fired power plants in this part of the country, named Oltenia region, that are still running, and I'm guessing that they will still run for a little while, at least. The government is doing some negotiations with the European Commission to prolong, extend a little bit the planned date of decommissioning of these coal-fired power plants. And we have also a large emitter in the steel industry. And not negligible, but we have cement industry that it's emitting around, we have 6 installations that emit between 600 kilotons and 1 megaton of CO2 per year. So it's not that much that we emit. But we have reduction targets. The reduction target is 85% by 2030, 96% by 2040, and 100% according to EU laws and strategy by 2050. And you will see now how the emissions have evolved in the past, how the emission reduction of emission was done, and that we are very, very close to reaching our target very early. I would like to say that this is because we have implemented some very, very good reduction emission strategies. It was the case, but unfortunately, the reason behind that is industrial decline of the country after 1990s. after we became, we got rid of the communism time. The reason for that could be a long, not very well governed privatization process, because many of the industrial installations in the communist time were actually belong to the state and managed by the state. Of course, we have emission reduction targets for every industrial sector. We have great targets for the energy sector, as you can see, which will be achieved once we are decommissioning the coal-fired power plants, and we increase, this is mandatory, to increase the share of renewable energy in the gross final consumption of energy. We have large targets also in the industry sector, including, of course, cement industry, steel and cement industry. We are also obliged to increase our negative emissions through land use and land change. Our decarbonization strategy, as recently at the end of last year presented within the National Energy and Climate Plan, includes, of course, energy efficiency, renewable energy development, nuclear energy development, renewable hydrogen production, increase of gas storage and natural gas extraction, with further development of natural gas infrastructure, but includes also, and I quote, this is a quote, promotion and co-financing of CCUS for vast emission reduction. Mentioning that refers to deployment of CCUS technologies in energy-intensive hard-to-abate industries, and that by 2050, at least 50% from the mineral industry, including cement, will be captured. As I say in the beginning, we have transposed the CCS directive, as everybody, in 2011. And through this, the storage was permitted onshore and offshore. After that, the competent authority in the field of CO2 geological storage, formerly known as the National Agency for Mineral Resources, regulating also petroleum activities, has issued specific procedures for exploration and storage permits, for granting exploration and storage permits. Recently, this law of CO2 storage has been modified at the end of last year to allow harmonization with petroleum law. And one of the amendments introduced is that exploration will be not needed for oil and gas fields at the end of life if they could be proven as suitable for storage. So they can apply directly for a permit, storage permit, not going through exploration. There are, of course, other amendments included. This was the most important for us as geologists and as interested in CO2 geological storage. Of course, there are some provisions to how the transport, the licenses of CO2 transport will be licensed by National Agency for Energy, the competent authority, regulating authority for the transport, not only for CO2. And now one of the recent premises for speeding up the implementation of CCS, CO2 storage, is that under Net Zero Industry Act, as you can see from this figure, Romania is the second, has the second largest quota in European Union. So after Netherlands. So by 2030, we need to store 10.25 megatons per year. This quota is distributed among three companies. The largest quota have been attributed to OMV Petrom, most important oil producer in the country, and Romgaz, which is the main gas producer in the country. And also the smallest quota is for the Romania is for the Black Sea Oil and Gas, who has some gas offshore fields, operates gas offshore fields, some of them. And this is from the side of our regulator, the reporting under Net Zero Industry Act. On the right side, you will see where the CO2 is considered to be feasible and permitted in Romania. And you can notice that apart from the Carpathian Mountains, everywhere is permitted, onshore and offshore. And here on the left, you will see some possible decommissioned or close to decommissioned wells that were reported by the oil and gas companies with quotas under NZIA. So I said that we have onshore and offshore storage possibilities. We have started to do research on onshore storage possibilities back in 2006, 2008, when we, GeoEcoMar, have been partners in EU GeoCapacity project. Back then, it was done by us, the estimation of theoretical CO2 geological storage capacity for Romania, only for the onshore part, yes, based, unfortunately, solely on public data, which is kind of scarce in Romania, being an old communist country where practically every information on hydrocarbon exploration, exploitation was considered classified information. No, classified. There is a classified. So there are different confidential, yes, of confidentiality. Classified. So there are information classified as secret of state, which is the highest level of classified documents. Then it's secret of, I don't know, secret of service, but all of this data were considered secret, classified, yes. It was possible to access some data, but very hard, very hard. I was, I made this exercise a long time ago. I'm not saying in the last years, but a long time ago was very hard to get this data without an order from the government or from, yeah. So we made this estimation of theoretical CO2 geological storage capacity in 2009. It's purely theoretical, yes, at the base of the estimation, capacity estimation pyramid. And with considering all the regional aquifers that you see with blue, and we said we have estimated 18 gigatons capacity in deep saline aquifers, including all suitable formations in these regional aquifers. Yes, and for hydrocarbon fields, 4 gigatons. I must mention that up until now, this is the only estimation of capacity onshore at national level. Different studies have been made at regional level and reduced areas, but this is the only done at national level. We have reanalyzed the storage possibilities on shore after geocapacity in the CO2 Stop project. And there you have the link where you can see the database for Romania. It's available on the site of European Commission. Offshore storage, yes, it's possible. Maybe it's a good idea since we had faced some public opposition in the last years. But I will not talk about that in this presentation. So we have started a research done on this Histria depression, which is on the Romanian exclusive economic zone in the northern part. A depression that geological unit where most of the oil fields are on the northern part. You will see this with the green. Yes, with the violet, there are some structures that were found to be non-productive during the exploration of the Black Sea, which started in 1979-1980s. So we have looked at those non-productive structures as possible deep saline aquifers. But we couldn't find all the necessary information to estimate the capacity for this geological unit. And in the past years, of course, due to an increased interest in CCS, CO2 storage, oil and gas companies have started their own research on the Black Sea. Now we are talking about projects. Yes, all projects. We have the very good opportunity in 2010-2012 called the Jetica CCS. Project was supposed to be a full chain demonstration project, the first of its kind in Eastern Europe. With the capture from a coal-fired power plant, one unit of the coal-fired power plant, transport with onshore pipelines, storage, deep saline aquifers. We have completed the feasibility study, actually financed by Global CCS Institute. Thank you for that. And with some help from the Ministry of Economy of that time. Joe Comar was actually the coordinator of the storage part of the feasibility study. We have selected and characterized 2 potential deep saline aquifers. The appraisal was about to start. The project competed under NEL 300 program, was on the waiting list, then the government changed, and you know the story. Yes, unfortunately, it's a good work. Maybe we could benefit from that work because that work is done and continue somehow. It's a potential project, not with the to take the CO2 from Turceni power plant, which should be transformed somehow in a gas-fired power plant according to the papers. But hopefully we will see the transformation from coal-fired power plants to gas-fired power plants. Gas is very important for our energy stability. Of course, it is very important considering the geopolitical situation. So, we do not have a operational project in Romania for CCS this time, so I will not present you a very good example. Maybe some learnings you can draw from it. Lessons learned. Governmental support is very important, and yes, governments can lead to projects being stalled. It's essential. And of course, public support. It's important also to disseminate information about the projects as soon as possible. So, according to what was reported under Net Zero Industry Act, because I said for this presentation I will, of course, give you only public data and what I can find as not as a general public and what I've known from other projects that are public. We have two flagship projects. One is a joint venture from OMV Petrom and Heidelberg Materials, which is planned to store in a depleted gas field storage of 0.5 megatons per annum, what is produced from Heidelberg Materials. Heidelberg Pieni, because we have several cement plants. And one is a project coordinated by Holcim, which supposedly will capture and store 1.2 megatons of CO2 per year from multiple sources. Unfortunately, we are waiting for the first round of Innovation Fund was not that good for this project. So we are keeping our fingers crossed for the second round. We hope that to see these projects operating in Romania. Yes, there are some intentions for CO2 transport projects. Another important thing for the storage part, which is essential for a CCS project, is that according to information, public information, the Black Sea Oil and Gas, who remember you also have a quota under Net Zero Industry Act, have the plans to use their gas fields as offshore fields for CO2 storage after their depletion. So that were the actual projects waiting to happen for a lot of time. You maybe see my frustration that it's been a long time since I'm waiting for an actual project in Romania, but in the meantime we have made a lot of research and we participated in a lot of international and national research projects. The story of research on CO2 geological storage of GeoEcomar and Romania also started in 2001 with the affiliation, I will be fast, Ala, with affiliation of GeoEcomar to Energ network that Ala mentioned in my introduction. And then continued with our work as subcontractors in other projects, and then EU capacity CO2 net east under FP6, then FP7 CO2 stop, ENOS project, Horizon 2020, strategy CCUS, we are part of that. We have also been involved in all of the ACT calls, EcoBase, Alliance, CCUS, REC-CO2, and Action. And recently, we are involved in CETP program within CTS and the Ramonco projects. I have a poster on CTS Black Sea scenario in the back. And more recently, or in the same time, we are part of Eastern Lights projects coordinated by Holcim Bulgaria. And we are looking also at cross-border cooperation on CO2 storage. Under national projects, I mentioned that we were, in fact, coordinators of the storage part of the feasibility study. We coordinated also the national plan for carbon capture and storage time horizon 2020 financed by the Ministry of Economy. And we have run multiple projects funded by the Ministry of Research under the core program for national research institutes. In the recent years, we have mainly focused on environmental monitoring, testing, methodologies, and methods for environmental monitoring on natural analogs from Romania. You will see the picture with my field, with my colleagues on the field. All of these projects are described on the poster, the other poster that I have in the back, if you want to check. I mentioned that there is also research on CO2 capture. I cannot give you all the details, just a few projects that I have been informed by our partners from University of Polytechnica University of Bucharest and Babes-Bolyai University from Cluj. They are involved in national projects, international projects, and they have also laboratory test facilities for CO2 capture. Calcium looping laboratory facility at University Babes-Bolyai in Cluj, and an experimental capture installation with membranes, amines, something, in Polytechnica University from Bucharest. I'm not a specialist on that. We were also involved in a joint project under Norway grants, hybrid solvent. I can provide more information as needed. I will not tell you this, what is this on the slide. Yes, I forgot to put some takeaway messages, and it's hard to formulate them. Yes, we have good opportunities for implementing CCS in Romania, as I said in the premises. We have high obligations under Net Zero Industry Act. We have the opportunity, this can be an opportunity and a challenge, the high obligations under Net Zero Industry Act, since you have seen the level of emissions. And yes, it will be tough until 2030. Yes, we do not have a storage ban, so we can practically store everywhere. The simplest solve of this situation with the high quota under Net Zero Industry, under my opinion, would be to start storage in depleted gas fields. But there we have a problem because we have a long history on oil and gas exploitation, so a lot of wells that needs to be investigated. This will be a challenge. Also, so the opportunities can be also challenges. And of course, we need to assess and update geological CO2 storage capacity. This is a must because we cannot show the same data as from EU geocapacity. We need, there is some governmental support, but we need more. Governmental support is essential. We need to implement public information campaigns, strategies. We need to involve, educate the public to not be in the situation to face again public opposition, which is very hard and can stop all the projects. That's why when I heard about the example from US with that CO2 contaminating the aquifer, I was afraid maybe our media will find out, and this will be a stop of any project in Romania. 1 minute, yes. Yeah, well, yes, because the public opposition, which was very hard, and the media played a very important role in that, was based, apart from the particular situation with the political conflict that was in that area, argued that there is no onshore CO2 project in Europe. They want to experiment on us. So think about that. I don't know. I could say I'm very hopeful that we will see a project in Romania as we deserve to. And this is it from my part.
Alexander, thank you very much. It's really interesting example, country case. So we can see that even country without any bans permitted CO2 storage on offshore did not implement anything yet. So it is a great nota bene to us that we have to act very fast now to do something in reality. I have question one to Alexander. I remember you had the CCS club in Romania.
Yes.
How many stakeholders you have there?
Not much. Not much. I really don't know. I'm not involved in that.
But Geo Kamar is
founding member.
Founding member.
Yes,
yeah.
yes.
Okay.
But I'm not sure. I do not want to give false information.
I see. But how about these oil and gas companies? Are there? Do you know somebody involved in the CO2 club?
I really don't know.
You don't know.
I
Okay.
cannot give any information on that.
Any question?
Thanks, Alexandra. Very nice overview. Of course, obvious challenges. I have a question regarding, as we see some of the big CO2 capture and storage projects, and also the news from Latvia, there was a lot of industry involvement for making that happen. Of course, the state support was there. But like in Romania, I know there is a very, very active oil and gas industry, and it's been there for more than 100 years. And many, many big players are there. So are there no interest from the industry in, like, especially oil and gas industry, to actually pursue this in Romania?
Yes. I have told you that OMV Petrom is preparing a project with Heidelberg materials. Romgaz is doing its own research, and Black Sea Oil and Gas just declared that, declared some recently, that they would consider CCS CO2 storage for their gas fields offshore. So there are plans, and they are doing actually a lot of research these years.
Okay. So they are involved. So sorry, maybe I missed it somehow.
Maybe I did not explain.
Okay, thank you.
But what is missing, and I forgot to mention this earlier, we need support not only at strategy level, but also, I think, financial support from the state. It cannot happen without this. Hope to see that.
Thank you.
Unfortunately, this problem with financial support, it is still in all countries developing CCS, also in Western countries. For example, when I estimated PCI projects from France, they wrote in their proposal no national financial support. What we know, the greatest example from our Baltic Sea region, it's Denmark. They really have national support. So now it's a message to our governments, parliaments, ministries, that we need national support also to technology, also not only regulatory support, which we now got in Latvia, but also financial support. And it's of course a great issue because our countries has some money collected from CO2 taxes, and this money is used for years, for example, in Estonia, for different targets, for wind energy, green energy, for electric cars, for everything, but not for CCS. I think they're more or less the same situation in Latvia and Lithuania. So the money for green technologies, for climate mitigation is available, but they are not used for CCS because CCS was not in national strategies and national energy plans until now in Estonia, Latvia, Lithuania. This is a problem, that we have to work more tight, more often, intensively with our governments, ministries, and parliaments. first to push regulations and then to get financial support, which is in fact source is available, but they are used for other green technologies. If there are any other questions to Alexandra, if not, then we are finishing this session. Mayur.
So thank you, everyone. We have finished a little bit early, so I guess some of you might want to do checkout. So if you want to do that, and then we can meet in the restaurant, same place where you had lunch yesterday, dinner yesterday. You're not gonna get the same food, okay? Apologies for that. It's been sorted, so you will have something different. So we'll meet there at around 1 o'clock, okay? Yeah. Yeah, so after lunch break, we have 1 hour lunch break, and after that we come back, there is a panel discussion, and then there's one speaker who will be online, okay? So I'll look forward to you after lunch, yeah? Yeah. So just Ella just pointed that in the schedule you see the lunch was planned for 1:30 because we have been running ahead of our schedule. So, but you guys can take some time to have coffee or something outside. But I think around 1 o'clock it should be ready. I've been told, so we can go there at the lunch place around 1 o'clock. Yeah. Thank you.
Sali Mohammadi, and today I will be moderating the panel discussion that we are going to have. The topic of our panel discussion is going to be today I will be moderating the panel discussion that we are going to have. The topic of our panel discussion is going to be today I will be moderating the panel discussion. I don't think there should be any echo. Okay, no. Yes, sorry for the technical problem. The topic of our panel discussion is going to be carbon capture, utilization and storage, CCUS, a solution to the climate change or a false hope. Recently, CCUS has been introduced as one of the methods to prevent the emission of the carbon dioxide to the atmosphere, and most definitely as a new technology and as a new idea, it is facing many challenges in both aspects of the scientific, technical, and also one other aspect that we can add is the public perception. These are the topics that we are going to discuss. We are the pleasure of having the panelists here. Madam Alva from the IM Law, Mr. Carlo from Global CCS, Mr. Yanis from Bologna, and Mr. Eugene from Wyoming University, and also Professor Sayuri gave the pleasure, even for that she was traveling to be a part of our conference. She is a part of Asian Development Bank, and she's working on the financial aspects. First, we will begin with the Mr. Yanis to give the introduction about himself, and also he's working in the field of the aspects of industry aspects. So I would be grateful if you can introduce yourself and also give the introduction.
My name is Yanis. Working? Yeah. I've been active for a couple of years on carbon management topic in Baltic region, and I think the progress is actually quite surprising even for me, as many elements that are needed for CCS and CCU to some extent deployment has progressed well. We see that even here we have participants from 3 leading universities from Baltic countries. We have industrial players. We have scientists. We have transport operators. And what the next steps basically is to implement and connect those dots in real life scenario, bring costs down by scaling technology, by making economy of scale, certainly following the climate targets. That is, just to remember that that's why we are doing this. And safeguard industries, even the local communities that will be around both carbon capture projects but also carbon storage projects. Ensure that just transition is real, that is not just nice political word, but public perception is ideally as it is in Norway, when they basically go out and celebrate carbon capture storage projects because they have the knowledge what it actually means. There is no fear or uncertainty about it, and I think that is the good basis to start, the knowledge that we can bring to the room. And I will stop here for now.
I just add one thing. Mr. Yanis is from Latvia. I know that multiple times it was mentioned during our conference, but for our audience who are new and watching us from YouTube, Latvia recently actually removed the ban for the carbon storage, and I think it's a pretty good news, which everybody can celebrate it. Yes, next panelist, Mr. Eugene, if you can provide introduction to yourself and the work you do, and also an introduction to CCUS for members who are, are not familiar with the concept of CCUS.
Sure. My name is Eugene Kholobnyak. I'm a director of Hydrogen Energy Research Center at the School of Energy Resources, University of Wyoming. But I'm also a co-founder of Avalon International Corporation. And so Avalon is a clean energy developer. We are taking basically lessons learned from my time in research and development, working on CCS technologies and trying to put our money where our mouth was. So now we're trying to commercialize CCUS on a large scale. My experience mainly comes from continental United States and Canada. This is where the projects were happening, but we are also looking into projects outside, and we believe that Baltic region is one of those key points on the map where we believe the next developments should happen. That's why we're here. In terms of what I think about CCS and CCUS, I'm fully committed to it at this point. And that means that I definitely believe that this is not, according to the title of the session, I don't believe it is a hoax. I definitely stand behind the technology and believe that it could be moved forward and could be deployed on a large scale.
Thank you so much. Our next panelist is Mr. Carlo from Global CCS. He has a very deep, actually, contribution in the business development aspects and also very many contribution and cooperation with other countries. I would be grateful if you can explain about your activities. And
thank you very much, Partsa. Yes, I'm Carlo Maccherini from the Global CCS Institute. I'm the Senior Regional Manager for Europe, which means that our team based in London is working on focusing on different pillars such as advocacy, making sure that CCS is always relevant in the discussion with governments. We focus on thought leadership. We focus on sharing knowledge about CCS, which I think at this stage is very, very important. And we focus also on creating a community of members in our case, but also of all the stakeholders which are active in CCS with a strong interest on CCS, because I think this is the key challenge now. We mentioned yesterday, I think it was Natalie mentioning the word cooperation. This is what we need now. I think in terms of giving an outlook about CCS and also something that has been discussed yesterday, Europe is in a very good position. The outlook is good. It's not a false hope. It's something that is happening. It's something that is going ahead. Then, of course, we need to analyze how it's going ahead and what are the drivers of this growth, which is pretty strong. We have a lot of projects going on in Europe. But again, we have 11 projects which are operational. We have 16 projects which are under construction, which means they reached final investment decision. The growth of it was plus 50% and more compared the last few years. This is something that was driven by an alignment of things of cooperation. First of all, policy and regulations, fundings, and this is something that I'm pretty sure we will discuss later, but funding is crucial to have projects which become operational. Knowledge, sharing knowledge. This is the best way to face objections and to have a good discussion about public acceptance. And then, of course, I would say, having good opportunity of sharing with the whole community, because what's happening now is we are having very good business cases in order to scaling up the economy of CCS and CCUS.
Thank you so much. I really appreciate. Our next panelist is Professor Sayori from Japan. She has been working on the financial aspect of the climate change activities. I would be grateful if you can provide an introduction to your work and also to the region that you're working on that?
Yes. So I'm from Japan, and I also work with a lot of Asian financial regulator to cope with climate finance, to develop climate finance. So let me talk about CCS. So since I'm from Japan, first let me talk about Japan. So a couple of years ago, in Hokkaido, northern part of Japan, the Japanese government did CCS experimentation. Basically, carbon dioxide generated from hydrogen supply from oil refinery facilities. And then I think it's because there's not much economy of scale. It was extremely expensive. According to some estimate, one carbon dioxide carbon dioxide, the cost was 300 to 400 US dollars. So extremely expensive. But because Japan and Asia, we are so much depending on gas and coal, so we need, I think, this kind of technology. So Japan last year passed a law. It's called CCS business law. Basically, this gives some incentive for storage entity, and then kind of licensing system, and they decide which location in Japan they can do a CCS experiment. So they are now already selecting some area near Tokyo, carbon dioxide generated from industry. And so they may start. But the one issue is that almost all these, pilots cost supported by Japanese government. And because Japanese government has a lot of big debt, and then, there is a lot of uncertainty how long Japan can do this, through their budget. And also in Japan, carbon pricing is still very low. It's just like a $10 or so. So, I think Japan is going to strengthen carbon pricing from next year, but it's very difficult to have a very high carbon pricing. So at this moment, it's not clear whether we can do this, on a much broader base. Now, looking at Asia, as far as I know, China is quite active because China, they have a lot of a few very big SOE oil industry. So they are doing some pilot project in their oil field. That is what I hear, but I don't know about the cost. Another interesting issue is that the Malaysia is producing gas and also offshore. So Japanese government and Japanese oil company had an MOU quite recently with the Malaysian government and I think Malaysian SOE Petronas. And then the idea is, carbon dioxide generated in Japan, the transport to the Malaysian is offshore, and storage is there. So it's still extremely expensive. So nothing is really materialized, but at least they did a MOU. One more interesting issue is Indonesia. They are producing oil and coal. And recently, Indonesia passed a law which said 30% of carbon dioxide imported from outside of Indonesia can be storage in Indonesia because they have a lot of mining sites. And 70% of carbon dioxide should be stored. Carbon dioxide generated domestically within Indonesia will be stored within their sites. So we started to see some activity, but it's not so very active at this moment.
Well, thank you so much for giving the information. It was very interesting aspects that how Asian countries are taking actually their advances in CCUS. Our last panelist, Madam Alva, she is in the IOM law and she has been working on the legal aspect of CCUS. I would be grateful if you can give an introduction of your own work and your activities.
Yes, so my name is Alva and I work at IOM Law, which is a law firm that specializes in carbon capture and storage. And it's a really interesting field to work in right now because a lot is happening in EU and a lot is going to happen in EU when it comes to regulatory work. A lot happened through the Fit for 55 package. We saw the NCA, we saw the CBAM, we saw the CRCF. We saw a lot of regulation coming in this package to kind of support the CCS business. To see how it will be implemented is going to be interesting. To see the effect it will have on the business is going to be interesting. And it's also coming some new regulations in 2026-27, kind of to tackle all the regulatory gaps we have. We have a lot of regulatory gaps in this business, quite new. It's also a new regulatory field. So it's a lot to learn, and it's optimism, especially for me. I'm brand new into the business, so I feel like it's the right time to come into it.
Very interesting. We most definitely come back to that discussion. First question, I would like to ask it from Yanis. We have seen, we said that all the panelists are saying that CCUS is not just a hope. It's a, a solution that we have to invest in it. Even I read it directly from UK's Climate Change Committee. They have mentioned that CCUS is a necessity, not an option. Why CCUS is so important? Why we have to invest in CCUS, and how is it different from the other methods of the carbon mitigation solutions that we have already?
Right. So first, I would say that carbon management by CCS and CCU is not for all industries. Right. It's quite focused to hard-to-abate industries as the best solution. In fact, at Bellona, we have created like a ladder when we prioritize sectors where CCS would be the best option. And for many industries, direct electrification is much better. There is a huge room for circularity that we heard here earlier. Efficiency, renewables, and so on. But for some industries, there is no other options as carbon capture. That's first thing. So next thing is make sure that cooperation is effective. And we have, if we speak about the regulations, then there is embedded open access to infrastructure, to pipelines. We aggregate the volumes. We see how to bring costs down, because for hard-to-abate industries like cement producer, that is not their core business. That is basically expense position in their books. So, in order to make those companies competitive, but also safeguard environment, we need to make sure that it's organized, coordinated, regulated in the best possible manner, at the same time, in a simple way. And most importantly, the regulation and support mechanisms should be consistent so that companies can rely that there is no sudden changes in regulations after.
If the companies want to invest in the CCUS, for some companies might be the other solution be using methods that produce less carbon dioxide. Is it possible for all companies to adapt into the solutions to produce less carbon dioxide, or some companies, they always are the producer of carbon dioxide and CCUS is the only option for them?
Can you give me an example?
I mean, for example, I know that cement companies producing carbon dioxide. So I think Alexei has discussed about the using blue hydrogen as a, so it would be more efficient even than and cheaper than green hydrogen, and at least we can receive energy. But in order to implement it, we only can do it through CCUS. If we do not use CCUS, other methods cannot provide sufficient hydrogen or resources for us. So it seems that CCUS for some companies to reduce their carbon emission is the only solution. Is that right? Am I right?
Well, I'm not sure if this question for panel, as the Excel table would give the right answer. But what I can say now is that it all depends on the life cycle analysis of production, and if we can use renewable energy for better, more effective products than blue hydrogen, then I think that's the way to go. But I think it's each plant specific decision to make.
Understand. Thank you so much. Next question from for Eugene. Well, we know that CCUS is used and by UK committee and many communities in the world. It is mentioned as well, important option that we have to invest in it. But aside from providing an opportunity to reduce the carbon emissions, would it be possible to form an economy around this climate carbon mitigation solution, or is the type of solution that always money and funds should be injected to it and always going to need government support, or no, at some point it can be independent and it can be a producer itself?
That's an excellent question, because I believe that there is a possibility to actually move away from strictly government support, although without government support it is really difficult to jumpstart the projects. So in the United States there is a different kind of paradigm about thinking about how to construct a CCS project, and also what is allowable, what is not allowable, both as a kind of license to operate, meaning the society approves of it. So I would actually have a good discussion about this, I feel, with Yanis, about what is allowable, what is not. And we see, for example, as Avalon, we see the solution around making CCUS projects or CCS projects is around making anchor projects that do produce something moving forward. So this something would help to create a cash flow and hence reduce the dependence on government support. In our case, we definitely, for example, we were developing a facility in near Corpus Christi, and this plant is looking into implementing CCS as a part of the operational scheme. We are looking to produce blue ammonia as a result, also a few other projects, but meaning that will have the CCS component, but will produce from natural gas or other similar oil and gas, petroleum coke, for example. That's another option that could be used in the process. We basically create a value-add product for something that is not very expensive, meaning electricity prices, natural gas prices are relatively inexpensive in the area. We can take advantage of that today, ship it or use it in the internal market, and then also create a CCS hub and take other CCS sources to our hub. Because we also are developing an MOU with the power producers right now, and they are thinking about putting the CCS in CCS component and therefore sequester CO2 on our hub, because otherwise it would become prohibitively expensive because of the capture cost, because of other costs, because of the knowledge about specific operations, because of also liabilities and number of other issues for these additional sources. It doesn't make sense based on their operations to go into CCS field. That's why they choose to play with others and implement the CCS strategy through partnership rather than through their own creation of their own CCS facilities. And so that kind of long discussion, but I believe there is a way, a little bit diversified, looking into diversified business models, maybe adding the circular economy and not other things could potentially make projects more sustainable.
Thank you so much. The next question is for Carlo, and if Alva and Sayuri also you want to add something to it, most definitely you can mention it. As Eugene mentioned, the possibility exists for the new technologies to become independent and work, especially in the field of CCUS. But Eugene mentioned that it requires government's support and fund to make this jump and develop the business to be independent. Since you have experience in with the global CCS and you are experienced with many countries, especially in Europe, what initiatives are formed to provide this support for the companies who want to invest in the field of CCUS?
I can give you a very European point of view in this case, which is that, of course, the economy already exists of CCS and CCUS in Europe. Now the challenge is scaling up the economy. And there are quite a lot of initiatives which are in places where the government support is always needed. So I would say that in this case, of course, there is an innovation fund, which is granting funds to projects. But then if you see where these projects are operational, or where they reach FIDs, this is where there is a strong support from each government. So every single project which is operational is mostly where, or where is under construction, is where contracts for differences are in place. Contracts for differences is a mechanism that is used by government in order to fill the gap between the installation cost of the project and the EU ETS, which is basically the carbon tax, the price assigned to each emission. That's where you need to go, because the problem is that at the moment, if you don't have this kind of mechanism, you are not able to de-risk for the emitters. So the emitters need to have as a priority basically the risk in the project. And that's when the government are supporting, and that's when it's working, and it's working well. Now there are very good news, because we have seen it yesterday in the presentation from the Polish associations. They are discussing CCFDs, contracts for difference, for 27-28, which is a very good news for the Baltic region, because of course this is what is necessary to have projects operational at the moment. We have other countries in Europe which are discussing contracts for differences. We have Greece, which is working on it since 2022. And hopefully we will have more countries following. We need to have a roadmap which is still has to be developed by governments. And also very good news from Latvia of having CO2 stored in Latvian soil. Also very, very good news. So I think that at the moment, on the short and medium term for Europe, the economy, the way we can scale up the economy is through a strong support from each government. Strong support means also having the possibility to discuss public acceptance. We have seen that all the countries which are pretty active, they have a very good strategy in order to share in knowledge. Yesterday was mentioned, when we were discussing about public acceptance, do you have public acceptance issues? Ask the Danish. That's the best answer, because of course what they did, it was amazing in terms of doing 180 and going from completely against CCS to having CCS allowed, and an operation, an FID project, which is Greensand.
Interesting. Alva, if you have something to add, and it would be interesting if you can discuss about the legal aspects also, because this topic might be a little bit foreign to many. Yes. That what does it exactly include, and what are the legalization aspect in European countries?
Yes, so the legal aspect of the financial incentives is not quite there yet. We have the ETS directive, which you mentioned, but the price is way too low. So that's why the government support is needed. As I talked about yesterday, we also have the voluntary market for biogenic CO2, which is now being discussed to kind of include into the ETS. So for biogenic CO2 in the future, it might be a market, a regulatory market for that. But currently, the only kind of financial incentive, now I'm talking about the EU, because that's my expertise lays, is the ETS, and it's not sufficient yet. So the legal aspect of this is a gap, and it's more policy-driven than legal-driven so far. But I guess this will also change when the business kind of gets up.
Thank you so much. So if you would like to add your point of view from Asian countries, especially Japan, regarding this topic, supports from Japan, or how your government is trying to facilitate the process of investment in CCUS.
I see. Okay, so let me talk about Japan and Asia. Compared to Europe, we are so much depending on fossil fuel. So 60 to 70% of our electricity generated from coal and gas. And we simply do not have sufficient renewable energy. So I think, Japan and Asia, because we are all committed to net zero, Japan 2050, like some country 2060, China, I think. So at this moment, I think priority is increasing renewable energy as much as possible. And especially Asian region, we are quite, I think, a lot of Asian countries are affected by the development in China. And China, also their GHG emission account for 30% of global GHG emission. But as you know, China is biggest producer in terms of renewable energy, like solar panel and wind turbine, and also electric vehicle. So China at this moment, they put a lot of priority on such kind of renewable energy and EV. And then they are still doing some experiment on the CCS, but the priority is not so much. And I think Japan also, CCS is important, but it's not the biggest priority. I think the main reason is, as I said before, it's extremely expensive in Asia. So, just a case of a Hokkaido, $300 and $400. And if we do it from industry, and, we have to find a place to store. But a small country like Ireland, like Japan, very difficult to find. Then we may transport to Malaysia or Indonesia, but then it's extremely expensive. So at this moment, it's so expensive. So I think it's not a priority at this stage. Yeah. But I think Asia, we have to be realistic because
you have 1 minute.
Sorry?
1 minute. You have 1 minute more.
Hello?
You can hear me?
Yeah.
Yeah, you have 1 minute more.
Okay. Yeah. So in Asia, we are depend a lot on the manufacturing sector, and then lots of AI and their data center. So we are depending on a lot of energy. So more and more energy supply we have to do. So we have to really, find a way to utilize this CCS. But at this stage, it's just so extremely expensive. So we haven't really talked, how to utilize this technology yet.
Understand. Thank you so much.
Could I just comment shortly? I forgot to mention the Net Zero Industry Act, of course, but we talked about this all the conference. That's like big financial entity. Yeah, sorry.
Can I also yes. On the same? I think it's very important topic. Financial support, just to kick it off. And
in 1 minute.
On this note, for example, there are many other instruments apart from national funding, EU funding, Connecting Europe facility. As example, in Latvia, Connexus operates this natural gas storage in Inčukalns that just received 40 million euro co-financing to modernize natural gas storage, basically on the same manner CO2 storage sites could be developed. And then there are different business models, like, for example, Schwenk today presented Bifrost project where cement producer basically comes in as a partner, almost as a shareholder in storage business development. So it's kind of really new market emerging, and there is different business models that we have not, traditionally used for developing infrastructure. Exciting times in a way, but what I want to say is that there are multiple different financial, models possible to make sites and transportation infrastructure possible.
Oh, thank you so much. Interesting topics that have been discussed. So maybe we can discuss about that. You have mentioned Carlo Danish that they were able to, change the public perception and invest on CCUS. We know that Nordic countries are pretty active in CCUS. And also Sayuri mentioned that China is working on carbon capture and storage. Then the question is come that in the global aspect, especially that Carlo, you have information about it. What is how countries are viewing the CCUS? Why Nordic countries are pretty active in CCUS and some countries are not? Is it that because these countries are waiting for others to go through all the risks and after that they take the advantage of this opportunity and then become CCUS? Or no, some Nordic countries are going with this view that, okay, we take the lead and we have the technology of this system. What is the difference and view in the global aspect and also in Europe?
Well, I would say that...
just in 2 minutes, if possible.
2 minutes?
Yeah, 2 minutes. Yeah.
Okay, I will try. I would say different reasons. So, of course, it can be driven by political sensibility. How important is the hard-to-abate industry in each country? And the potential to decarbonize it, of course, is always very important in order to gain job security. However, I think that what is driving at the moment is, of course, also a competitive advantage that who is investing in CCS now is getting. But we can see also on the other side, we have, and the other thing that we need to mention is about public acceptance that you have mentioned. Public acceptance is always easier when there is a strong trust in the government. So if you see the Nordic countries, there is always a good trust in the governments. And that's easier than to share knowledge. When the government tells you something is usually when you trust them. So that's the thing. On the other side, the good news is that now we have good business cases. The Nordic countries, other countries also all over the world, they have created amazing business cases, both from a technology point of view, but also from a regulation point of view, and also from a funding point of view, which means that if now Greece is studying CCFDs, it's because there are CCFDs in place from other areas, and they're working. So still, from a cooperation point of view, that's where you need to go. You need to take inspiration from what has been done before, and there's nothing wrong with it. And the other thing that is also very interesting is the Net Zero Industry Act. Now, of course, at the moment, it's something that is based on decisions coming from the countries where they want to go in terms of regulation, in terms of funding. Now you have obligations. So which means that there are countries which are not considering CCS or are not advanced as much as the others, that they will have to fill the gap. We have discussed this with Romania. It's a very interesting development, but it's also a big challenge because some obligations are very, very ambitious.
I understand. Then maybe Eugene, also you can give explanation because in the map that Carlo yesterday shows that North American countries are pretty active in CCUS, South African countries are not, and we most definitely also ask Sayuri about Asia. But what is making these countries so different to be so active in such research? USA is always famous for their always being leading in the new technologies. So what is the making difference? How?
For United States.
For now, we ask for Eugene, and after that we come to you, Sayuri. Yes. Okay.
So for United States case, I'm not sure if United States is leading, but we do have very concise and also bipartisan policies in place that govern CCUS at the moment, and that helps quite a bit. With this consistency, also staying through administrations, it actually helps for CCUS case. So I hope those policies stay in place, because at the moment one of them, and this is related to Clean Air and the Clean Air Act, is in jeopardy, basically. So hopefully it's not going to be repealed. If this is repealed, then a lot of projects and hundreds of billions in capex are going to be in jeopardy. So if that stays in place, that would be great. But I think the reason for all of those projects to move forward before, in the first place, was very concise, very consistent policy all the way throughout that helped, and also trust in government that helped investment, and helped projects to understand what they're going to be dealing with. It was basically essential, I would say.
Thank you. Then, Sayur, we're coming to you. I have been previously to Japan. I have discussed with some Japanese oil companies regarding CCUS, and they have mentioned that, they want to do projects, and it seems that Eugene and Carlo, both of them, mentioned that trust in the government. Is it that there is not trust in the government? How Japan country is imagining itself in this competition between CCUS in the Asia? Is Japan trying to overtake China, or they are? What is the objectives? Yeah.
So there is no competition yet in terms of CCS because it's not really prioritized. But can I share the challenges Japan and Asia are facing?
Sure.
So as I said, we are depend so much on the coal power plants. Still, some countries, increasing the number of coal power plants. In the meantime, like G funds and then a couple of NGO and also ADB, they try to provide money to facilitate the closure of coal power plants much earlier than their regular maintenance period. For example, if they have 30 years, let's close 10 years before so that they can at least save carbon dioxide emitted to the atmosphere. So, and that is also priority. So, we need money to accelerate the closure of coal power plants. And then we have CCS, right? Let me explain you the challenges we are having. So before we talk about public perception, there is a quite complicated discussion among climate policy expert and energy expert. Because, right now, we want to use CCS, not necessarily for industry. Most important one is for our energy. So basically, fossil fuel electricity. That is the biggest priority. And then, experts say, what's the difference between this use of CCS and, carbon lock-in? So, and in the meanwhile, we want to try to, close the coal power plants earlier, right? So it's not really clear, if we promote CCS, it just means we are kind of, maintain these coal power plants for long. So we haven't had enough discussion yet in Asia. And so there's a lack of clarity here. So I think part of because of this, there are some hesitance in some Asian country with regards to, promoting this CCS. Unless we have a clear, phase out plan with regards to coal power plants or, how to avoid carbon lock-in. There is a lot of uncertainty and also a lot of criticism. So that is what they have. So about the perception, very quickly, the public perception. In case we have to find a storage of carbon dioxide in Japan and near Tokyo, this will be the biggest trouble because, we have a lot of earthquake, and we are expecting big earthquake anytime soon. So even though, the scientists store the carbon dioxide underground very deep, for the public, it doesn't, they don't care. So they worry, even for the nuclear power plants, reopening after this big incident takes a lot of time and still a lot of criticism. So just this idea of storing carbon dioxide underground is very challenging.
Understand. Thank you so much for you mentioned two interesting ideas. One is that regarding earthquakes and also the carbon locking, which we will come back and ask this question from Yanis and Eugene. But now that you have mentioned public perception, I would like to ask Alva, what is the public perception in Europe and how these countries are trying to change it? What are people exactly are worried about CCUS and why this negative public perception exists at all?
Yes, I can try to. I think we already talked about that in the Nordic countries it's quite good perception. And we also have talked about Germany being a case with bad public perception and also how much that stopped the CCS business in Germany. So how important it is to actually focus on public perception. It is really important. And I think we already been to the reasons for why it exists. I think it's a lack of information or lack of explaining what CCS is in simple terms. Me, myself, not being a scientist, have struggled a lot to try to understand what CCS is. And I remember when I saw the first keynote speaker, when he talked about the model he had, the CCS model.
Martin.
Yeah, no button. I saw that live, and then finally I understood, okay, it is this easy. So I think we have a tendency to kind of over-explain it to people that are not scientists themselves. So I think that kind of difficulty of communicating what CCS is, because it's a brand new business, and it's not easy to kind of go into if not somebody is kind of holding your hand into it, if that makes sense. So I think the lack of information and lack of explaining it well is a reason for public perception, definitely. And I also think this mentioned yesterday when we talked about the public perception presentation, that for many it's seen as a continuous for oil and gas. It's kind of it's not the right solution for the climate crisis. It's just like a shell kind of. So and I myself had this view before I went to this business. So I think there's something in there as well to kind of communicate it as a climate action tool. It is. And I think now we have come so far, sadly, into the climate change that I think this point might not be as important as it was in the beginning of CCS discussion. I don't know if you have anything else to add.
Yes, thank you so much. If you want, yes.
It's also kind of a little bit more simplistic view from in layman terms. So we used to not care about things as much as we care today. And I think that's, and I'm not saying it's a bad thing. I think we saw it with the implementation of the injection program for CCS in the United States. Previously, all the programs, and if you know the injection programs and protocols from previous generations, they're not as extensive and they're not as onerous as CCS. And there's no good reason for it, rather than that society grew up and we basically do things very differently compared to the early days, for example, of gold rushes and oil and gas exploration. It just was very different. Oil spills all over the place, and all of those fumes that are not that good for your health and the health of your children were just not a concern. And again, I'm not saying it's a good thing. I'm just saying it's a very different paradigm.
Alba mentioned it, or society mentioned it regarding some of the actually views that public has on CCUS. Well, regarding Japan, they said that okay, we have earthquakes. If we store this carbon dioxide into subsurface, and we have earthquakes, would it cause even more damage to countries that they have this risk? Or I know that in European countries they say that storage of the CO2 might cause changes in the structure of subsurface structures, and later on cause bigger damage. Or the other thing that also Sayuri mentioned is carbon lock-in. They say that okay, if we use CCUS and kind of, for example, we still using fossil fuels, and rather than emitting it again, we use CCUS. We kind of again depending on fossil fuels. You are not separating ourselves. How valid this ideas are, or they should really be worried this earthquake is going to cause more damage if you store, or is even, or if we are begin using carbon dioxide, we are going to be more dependent on fossil fuels? Both you and Yanis, if I would be.
You want to go first? Okay. So for the earthquakes, because again, I have seen firsthand the earthquakes and the effects. So public doesn't understand exactly what is happening, and so fracking causes an earthquake. It immediately is they don't like the ambiguities and the uncertainties and all of those things that are associated with the scientific process. That's not something that is that they like, and also they also don't have time. And I'm not saying again, I'm not blaming them for this. It is how it functions, and so you need to be able to explain to the public what is happening, and that takes time and also experience in doing so. That's number one. Number two is that are there really concerns? Unfortunately, the answer is actually not straightforward. It is not yes and it's not no. I would say it is yes to an extent, but if done right, with care for the site selection and characterization and understanding the region and doing all of this work and all of this work doing diligently over time, then the risk of causing problems in general will go down. So am I concerned about this as an engineer? If I have to sign under a specific sort of injection plan, yes, I will be concerned, but my concern is not really high, because I know that things can happen, but the probabilities are lower and it could be avoided with the careful planning.
Well, Yanis, you have experience in the Baltic region. Lithuania was a country that began storage of the CO2, but they banned it, and it was also banned in Latvia. So I would be happy to see your point of view.
First, maybe I will finish. I will just say a couple of words that in my life I have not experienced earthquake, and maybe I'm not the right person to answer this question. But I think we are in the region that has the very small risk with that maybe even place our region even more higher for the CO2 storage location point of view. And speaking of public perception, it's really I wouldn't be that negative about it because we have done surveys actually in Sweden, in Denmark, in Latvia. We will have results in Romania and Poland very soon. And it's not that people say that they don't trust the technology. It's that they are not that much interested in that. So it's not, it's not electrical vehicles that everyone use or potentially will use. It's rather industry-specific thing. And we have, as I mentioned, the natural gas storage. Natural gas, I mean, completely different risk level comparing to CO2. And we have, villages next to that storage location operating for decades perfectly without any problems, and the villages are actually happy that they have workplaces there and no substantial risks occurred. So I would not kind of put public perception as with the negative color. It is just something to address, something to share the knowledge, something to educate. Even the questions like you gave about the earthquakes, just so that we remove, some kind of lack of information.
Yes. Since Arvo, you're also going to talk, I maybe can ask last question from you also. You're going to talk about the public perceptions. Along with that, you can answer both of them. You have shared information regarding legalizations in European countries, especially in Germany. And we understand that many of these governments are understanding that, okay, CCUS is important, and at the least we have to take some actions to see how impactful it can be. But why the legalization process is taking so much of time? Is it it is very natural and it is something that we should expect, or it is that things are really going slow and there is not enough of information or can push from either public or the scientific community to make it happen?
It's a complex question. Definitely, I think it's based on many things, to be honest. For me, right now, I feel like everything is going so fast, so I don't feel any slowness in regulation happening in the CCS business right now. So I haven't experienced the Death Valley somebody talked about in 2017. So I feel like things are really picking up. But I think the reason for that, I think Eva also talked about it in her presentation, is that we really got a kind of Green Deal burst in Europe in 2018, 2019, and kind of got that public and governmental kind of awareness, and also kind of push from the governmental side to kind of focus on the CCS business, because as we have talked about in this conference, the technology is not new, and it has existed for so long. So I think the reason why it's taken so long is it's also the reason for why climate change, like trying to fight climate change, is taking so long, because it's such a long perspective thinking. It's so hard to kind of put everything else away and focus on that right now, which might have effect in decades or even. So I think it's also just a problem generally when it comes to climate mitigation tools. But to end on a positive note, I think definitely we are in a good pace right now, and I think a lot is going to happen now, and it's a really interesting field to be in right now. I know it's been a hard struggle for many people that's been in for 10 years, but right now it's good.
Because I have seen that you have showed me that European Commission just in 2024 signed some agreements regarding CCUS, and it was really strange that it is taking 7-8 years to make the decision. Even for that, we have the Paris agreements, and we have specific goals in 2030, in 2040, to, if not reaching to net zero, we at least reduce it significantly. So that was where the question was formed, that why it is taking even for European Union. You can understand for some country that might take. Germany is not very active, Portugal is not very active, but as a union, it was very new that it is taking so much time for them to make a decision.
Yeah, I think it's a hard question to answer why it's taken so. Do you have a comment? Yeah, please take over.
The comment is, actually, I would like to see it on a more positive note. Let's think about 2024 and let's think about the elections. When an election at the European Commission, European Parliament happens, for months and months you block everything. You don't do a single law, you need to start again. They were able to implement the Net Zero Industry Act before the elections, and it was made on purpose, basically, because so that it will be active now. Otherwise, the risk was to have this delayed for another year. So, yes, the European Union can be slow. Yes, policymaking is, in these cases, slow, but let's see the positive side. What we had last year, it was an example of the commitment to having an implemented Net Zero Industry Act and have it now. So this happened right before the elections, and it was on purpose.
And also, just to show Denmark again, also really changed around their regulatory framework in few years. So it's possible once you kind of get that spark and you use it and you take it as before the election. So you do it in a political will. I think that can happen.
Yeah, so the politics are very involved in this one. Yeah, that's. Then this is the last question. Not much of time remaining for our conference. Then I would like to proceed to the final part of the conference, the final thoughts of the panelists. We begin with Sayuri. Please, if you have anything that you want to include and add, please mention them in 3 minutes.
So I think it was good that I learned there are a lot of positive view on CCS, especially in Europe. But I think please understand Asia is a bit different, very different sentiment. Partly because we are so much depending on manufacturing and energy, and also public doesn't really understand why we need to decarbonize. The idea of reducing GHG emission is still not well understood by public. So strong resistance even to reduce GHG emissions. So if we want to explain more about CCS, it's more even challenging. So I really hope that, Europe, I hear that, consumers want to buy low carbon products and services, but nothing like that in Asia yet. So it's very public perception and also environment and energy specialist criticism are quite important. I think we really have to sort out, how to decarbonize our economies, to what extent we can use CCS. That kind of better understanding is essential before we start to promote CCS in Asia.
Thank you very much. Eugene, if you want.
You mentioned for the new generation of CCS experts coming in, right? That was one of your requests. Yeah, so it's a challenging field. There's no doubt about it. But because it is challenging, it is also could be very fun. So there are many opportunities for new generation. There's one of the things that is not kind of solved on any sort of consistent basis is the monitoring for CCS projects. Monitoring storage monitoring for CCS projects is there's no company that actually governs CCS and offers the one-stop shop for CCS monitoring, and no Baker & Hughes, no Schlumberger, nobody basically offers that. So I think that's one of those great opportunities for new people who come into this ecosystem to function.
Thank you, Yanis.
Just very shortly, every one of us can see kind of evidence of this market evolving. I myself, I see that my stakeholder list increases. That means that that the market is growing. Yesterday we visited a startup company that produce raw material from CO2 and so on and so on. So, be it innovations in capture technologies or transportation, logistics, usage, storage. It's quite exciting, market right now, and I'm certain that the world we are living in will be much different in 2030 than we are today, and I look forward to it.
Thank you so much.
My final thought is, well, from one side, I would say CCS and CCUS are not the silver bullet to fight climate change. They are part of the solution. So they go together with renewable energies, of course. They go together because they are all needed. So also in terms of public perception, this is a message that we should send. If we are for CCS, doesn't mean that we are against renewable energies. Then the other thing is that, yes, it's a very exciting moment for CCS and CCUS. It's very exciting because, of course, there is a cooperation. We have policy and regulations in place. We have funding mechanism, and this is bringing to a nice growth. Nice growth means also new opportunities for the economy. It means securing existing jobs, because this is also very important. When Yanis was mentioning, people are maybe not interested. This is something that should be of interest. The CCS and CCUS are securing jobs and are creating new jobs because, of course, new technologies are we are developing new technologies. We are creating new job opportunities. So for a young student, I would say it's a very exciting moment to consider CCS technologies for their future.
Yes, and my final thoughts as well. To kind of go back to the legal regulatory view, is that a lot of regulatory framework has come now and will come, but I think it's also important to highlight that the framework doesn't need to be perfect in order for a project to start, and that the project will affect the frameworks, and you have to learn from the project. So just have that in mind when we talk about regulation. It's a lot of good framework going on. It's a lot of gaps there as well, and this needs to be updated. It's like a cycle. It's not a regulation, then you are finished. So that's a note. And also just for students, I think it's a really interesting business to be in, because you actually have the opportunity to have an effect on it, to be honest. You can actually really be where it actually is happening right now, and be kind of evolving with the business. So don't hesitate to join it. It's difficult, yes, but it's also interesting.
Thank you so much, everyone. I just add one thing myself, the things that you have mentioned. I joined also working on CCS project. And when you mentioned, it was even when I joined, CCS was a completely new topic. It's rarely known. And I think one of the things that I hope this conference and these panel discussions is going to help in that path, and also our next actions, is that kind of introduce CCS. It is a very unknown topic. Rarely it is known by the people, and it seems that this climate change has also has a negative impact on the people's view on CCS, that okay, now we are taking this CO2 from atmosphere, storing on under subsurface, or is it feasible or not? Something that I think it should be addressed. Also, you have Carlo mentioned that the job opportunity that it creates, the economic aspect, I think it would be something very interesting for governments, because usually governments care about the economy more than the climate. They have to compete in this global competition. So these are the things that it would be interesting to have a view on them. Thank you so much, Sayuri. Thank you so much, Eugene, Yanis, Carlo, and Alva for sharing your valuable opinion and comments. Thank you so much, everybody, for listening to and participating in the panel discussion, and our also online audiences. Thank you so much.
Bye-bye.
Well, now we have come towards the end of the whole function. Thank you all for your support, for being here till the end. I really appreciate. I would really like to thank all the speakers and the participants on the behalf of BOSREC board and advisors. Some of you have seen them. They have been actively participating and supporting the event as conference chair. So I would like to give first a round of applause to the board members and advisors who have been very supportive throughout the event. And of course, big thanks to all the speakers who took the time and have traveled all the way to Estonia and have presented different overview of different things. We looked at the policy side of CCS. We have looked at the research and innovation side. We have also looked at the advances in Baltics and Nordics. We looked at the industrial development, and also, of course, again to mention the news about the legal aspects and the changes in Latvia. I hope you all enjoyed the site visit, to where you actually see some of the carbon utilization, and I hope that in future you will be attending the future Baltic Carbon Forum as well. And before I wind up, I would really like to thank my students and researchers who have been helping to put this together. So Parsa, Sargam, Shruti at the back, and Pius on the camera as well. And I would like to also thank Rashid, who is also sitting at the back. They have been working behind the scene, organizing some of the logistics part. And it's very unique. My wife also showed up, and she is here she also helped me with quite a few things. So thanks, Evelina. And also, and Mike has been here taking pictures since yesterday. So thanks to Mike as well. We will put all together the pictures and we'll share with you, and you guys can download and use it for your post or something, or just for your reference. So thank you all, and I hope you have a good journey back home and a good weekend, and I hope to see you next time at the next Baltic Carbon Forum. Thank you.